ladies and gentlemen, ahoy! Ahoy, ladies and gentlemen, ahoy! Give me a second now. I need to get my story straight. My friends are in the bathroom getting higher than the Empire State. My love, she's been waiting for me. Have across the water, sunglasses, asking about a scar, and I know I gave it to you months ago. I know you're trying to forget, but between the broken promises and so if by the time the bar closes and you feel like falling down, I'll carry you home. Tonight we are young. What is up, everybody? Gamers and gents. Dude, I don't know why my hair is just so weird, man. I can't get, like, from the front it looks fine, and then from the side it looks weird. Something about it just looks kind of weird. I also have this insane brow bridge right there that needs to go back a little. But anyway, what's going on? I just microwaved some tea. So if by the time. So what's the news today, ladies and gents? What is the going ons today's? What are the happenings for today's? Well, today, what happened? Let me tell you all about it. Okay, what the frick diddly doodah happened? Oh, is there a Steam sale going on? Now hold on, do I have an excuse to spend $50? Even though I only have a MacBook? So like, what the fuck? The string broke, man. Well, the string is still there, but like the paper thing broke, man. Oh, so I gotta just use the string to put it in this hot water. So if by the time the bar closes and you feel like falling down, I'll carry you home. I don't know why that song is stuck in my head, but it is. But it is. Oh, only the Assassin's Creed series is on sale. Well, I already have the Assassin's Creed games both on PlayStation 3 and PlayStation 4. And I don't think people mod Assassin's Creed, do they? Let's Google that. Assassin's... Let me let you see the screen while I Google this. Assassin's Creed 2 mods? Do they have mods? Nexus mods. Play as British Jaeger? Visual mods? The Reshade, Rebirth Reshade, Eagle Patch, Anvil Toolkit, Deluxe Edition Unlocker. PlayStation buttons, Neural 1080p enhanced PC default controls, gently photoreal reshade, E3 outfit. Yeah, dude, there's not that much mods, and I highly doubt it's easy to actually install these mods. How to install. It's a 1-minute video. Is it easy then? Oh, do you just drag and drop? It looks like you use a mod launcher. Anyways, why are we even focusing on that right now, dude? we've got much more pressing matters at hand. And so what was I saying? I'm tired. The tea is really hot though. I can't drink this right now to get my caffeine shot, but you might see over here we got a couple of things. Just make the full white background. You might see we got a couple of things here, right? That we need to do. So what happened today? Today we had our solid state physics exam, midterm. Okay. I think it went okay. There were quite a lot of questions that I left blank. I think like one whole question I just left blank. But yeah. Aside from that, I think everybody did generally not great on that midterm, so I'm hoping that it's not that bad. Do we have another midterm? Are there 2 midterms for this class? There has to be, because I took this really early, right? Yeah, there's 2 midterms. The other one is on March 21st. So if we just ace the second midterm and the final, no problemo, okay? But yeah, anyways, yeah, because one of the midterms is worth 20%, so yeah. So I was like, what, 20%? So if you got an F for 20%, you still got 80% to make up for? That's quick math, bro. I ain't no math major. I'm a physics major. But I'm doing a math minor, I think. I have to check that, man. I gotta get that shit figured out. Let me put that. Let me put that in my long-term reminders. Long-term reminders. Shit, I still gotta check the... Fuck. Let me just put that in reminders then. Get math minor figured out. Check out some scholarship thing. Okay. Ooh. My head is hurting as well. You know what that means. You guys know what that means, okay? I don't think I have to remind you what that means. Okay, time to take some ibuprofen. I just realized that, like, if every time that my head hurt, I went off screen and did something, and I refer to it as you know what that means, I just realized that could be misinterpreted in quite a few ways, but no, I'm literally just taking painkillers, okay? I'm not taking any unprescribed substances, okay? It's just a painkiller. It's just ibuprofen. Ugh. My God. Alright. Popped that. Look at this. Look at this cool dish soap I got. It's like really blue. It's like a really nice blue color. I love this color of blue. Like, it looks like something that I could just eat. And I love the aesthetic of the bottle as well. Here, look. The bottle just looks cool, man. It's just cool dish soap. I never thought I would say something like that, but yeah, the dish soap is just really cool. Like, it caught my eyes. It also makes the kitchen sink look a lot better. Anyways, you guys wouldn't understand, would you? You wouldn't understand at all. You guys aren't dish soap aficionados. Oh, I had this music playing the whole time? I didn't even realize. It's good music, but okay. So, we've got a little order of operations to run through, okay? So we did our solid state physics midterm. That was whatever. Okay, it's done. Hopefully the curve is good. If not, we still have the second midterm and the final to completely destroy. So, other than that, we have our quantum mechanics midterm tomorrow, which we have done zero preparation for. So that's going to be fun. It's going to be a fun time. But get this solid state physics paper out of my face. I had some working. Get that shit out of my face. But anyway, so quantum mechanics midterm is tomorrow. My mind is scatterbrained, bro. You know this is not a good sign. Holy shit. Can this tea cool down already, please? So, quantum mechanics midterm tomorrow. The to-do list over here are the 3 topics that will be on the 3 questions for this 1-hour exam. So there's conservation laws, non-degenerate perturbation theory, and degenerate perturbation theory. So what I'm going to do is, and this is publicly on YouTube, everybody, 230 views, okay? I'm going to watch another professor's lectures because I understand so much better their way of explaining things than my professor. I'm not going to throw shade. I'm not going to say this and that. I'm not going to put some normative statement to it. I'm just going to say, okay, I'll just put it out on the table that I just understand the way that this professor describes it so much better. And his videos are freely on YouTube. Same exact course that I'm taking, 137B, okay? Maybe a different syllabus, but so yeah, we're just going to watch his video on 2 times speed. It's an hour and a half. So with 2 times speed, it's going to be like, what, 45 minutes? Because 30 minutes plus 30 minutes is an hour. 15 plus 15 is 30. Yeah. So 45 to, yeah. That's what I was doing. Okay. So we're going to watch this. We're going to watch his video on non-degenerate perturbation theory and then degenerate perturbation theory. And then we're going to look at some problems on conservation laws. I don't even know if those are homework problems. I don't even know. Were they homework problems, conservation laws? Yeah, it was a homework problem. Conservation laws was a homework problem. Yeah, okay. So then we'll look at the homework problem on conservation laws. And then, we might do some catching up with the other lecture material because there's these, I need to catch up to hyperfine coupling because I think next week we're going to be doing variational method. But whatever. Anyway, let's just watch this. So you're going to watch YouTube videos with me, okay? That's what you're going to do. You're going to watch YouTube videos with me.
Okay, this meeting is being recorded. Share screen. And now I will try the trick. Huh, it's working. Yeah, awesome. Okay, yeah. The problem was I have 2 networks here, and I had my iPad on one network and the computer on the other. Okay, everything seems good now. Okay, folks. So today the plan is to discuss perturbation theory. So here you can see it on the screen. Perturbation theory. That's the plan. And so the whole point of this perturbation theory is that the whole point is that we have some Hamiltonian H, which we can write as a sum of a Hamiltonian we know H naught plus some Hamiltonian we don't know H prime, and H prime is the perturbation. That's the thing we don't know, the new thing. And so the whole point is that we want to solve this equation. Okay, we want that. And so we want to know what are the new eigenenergies and what are the new eigenstates of this Hamiltonian that we don't know. Because we have this perturbation, so we have this new Hamiltonian. So the things is that we do know something. We're not totally ignorant. We have an unperturbed Hamiltonian H naught, and we know how to solve that. And we know how to solve that because we solved it last semester. You solved it in your quantum mechanics class. It's either the square well or the subharmonic oscillator or the hydrogen atom. It's some state you know. And so the question is, how do we get the things we don't know from the thing we do know? Okay. And so the trick is that the perturbation trick, and it is a trick, is that if H prime is small, the perturbation, then we can think of the Hamiltonian as the unperturbed part plus the perturbation, and let's multiply the perturbation by lambda. And the idea is to think of lambda as a variable, and lambda goes from 0 to 1. And so you think of the perturbation. The way to think of it in your mind is think of lambda turns on the perturbation. And so I want you to have a picture in your head because it's very physical. I mean, it's a bunch of equations, but there's a very simple physical picture. The idea is that you have your system, And this is the picture you should have in your head. Start with the unperturbed states. And the unperturbed states look.
I'm gonna just pause real quick. This is the main reason why I understand his lectures better than my professor now, is just because, look at this. He sets up very clearly what are the motivations, right? What do we have? What do we want to know? Like, what do we have? What do we want? And what do we know? Yeah. What do we know? What do we want? What do we want? What do we know? Okay. He sets that up, makes it very clear. And then now, before he starts diving into like exactly how you figure it out, and it's very theoretical heavy, very equation heavy. Okay, it's very quantitative, I think, is the word that you would use. But before that, he just gives a general picture. He's like, all right, let's think about the broad structure of what's going on, right? Because when you go to solve a problem, it's not like, let's say, for example, let's say my job is to increase the effectiveness of tables in a workplace, right? And let's say they hire me. They're not just gonna hire me, sit me in front of like a table and be like, make it more effective for the workplace. And then I'm gonna be like, I don't know, what do you mean? Like, what's the context? Like, what am I trying to do? And then I'll end up like adding like six legs to the table, putting in 10 drawers, everything like that. Whereas if the person who hired me to make these tables more effective for the workplace, if they just showed me the workplace first and then showed me the general picture of like the people that are interacting with these tables, then I would clearly see like, oh, it seems like a lot of people now, they're having a bad experience with these tables because they're getting back pain from sitting at tables for too long doing their work. So then my solution, instead of adding like 6 table legs, 50 million drawers, making it maple wood, adding varnish, whatever, instead of doing all of that, instead, now that I know the context of what I'm thinking about, it's like, oh, clearly to increase the effectiveness of the workplace, clearly this table just needs to be, I need to make it a sit-stand table because people are having lower back pain. And so with lower back pain, what can fix that? If you stand somewhere. Like, that, there's a very, humans are very good at problem solving skills, okay? We are very good at problem solving. The thing that we're not good at is problem solving with shitty prompts, okay? We are like these chat GPTs, okay? If you just write something, actually no, because chat GPT is good at like filling in the blanks. We're just like a language model where you write some prompt, right? And then it's like, if you write a bad prompt, I don't know how to solve your problem, okay? You got to present me. I can't make a good solution. I can't figure out a solution or understand how a solution works without knowing first really well how the problem is, okay? That's the thing. To have a good solution, you need to understand your solution very well. You need to understand the problem very well as well. Okay, you can't have like a genius understanding of your solution without understanding your problem at all. Okay, the only reason why we know so much about why 2 + 2 = 4, the only reason why we know so easily that solution is 4, is because we know what the problem is. 2 + 2. We know what that is. 2 + 2, 4. Right? 2 + 2, 4. See how I did that? But anyway.
Like this. Let me share. I have my unperturbed states, which gives me some quantum levels, my ladder of states. And I have my first state. And by the way, I did this picture last time, but I'm doing it again because this is so important. This is the basis of perturbation theory. And perturbation theory is one of the most important things in quantum mechanics. It's very important. So I have this state, psi1, E1, and I have my second state. These are the unperturbed states. My second state, eigenstate, psi2, E2. I have my third one. These are my unperturbed eigenstates. And I know them all from last semester. But then I have this new perturbation. I have this new Hamiltonian H. And H is equal to H naught plus H prime. It's a new Hamiltonian, and it has all its levels. The ones I don't know, and they're named psi1, E1, psi2, E2, psi3, E3, etc. And the idea is that as I turn on lambda, these states connect. This state somehow it morphs adiabatically into this state, and this state morphs somehow adiabatically into that state, and this state morphs into that state. And here, when lambda is 0, then I'm here in the unperturbed state. But when lambda is 1, I am now in this state. So in your mind, I want you to turn lambda on. Think of it as just slowly ramping up the perturbation. It's a very important picture. And the idea is that each of these unperturbed states can be connected to the perturbed state. And if this works, there's a 1-to-1 matchup. And so if this idea is sound and works physically, then perturbation theory is good. But I do want to say that sometimes this idea fails. For example, when there's a sudden phase transition. And I mentioned that last time, so I don't want to completely repeat everything from last time. But I am repeating this because this is the basis of how you conceptualize perturbation theory. I want you to have this picture in your head, the one that I drew here. This picture I want in your head. So if that picture doesn't make sense to you, then talk to me or the TAs or whatever. Okay, so the idea then of the perturbation expansion is that the idea then is if H is equal.
Look at that. Look at how we just, it's like suddenly now, if you look at this, looking at all this can be kind of confusing or whatever, but suddenly all of this now makes sense. Well, not really that. I'm kind of jumping the gun a little bit, but
the one that I drew here.
All of this will explain the working that comes after. I watched this video before, by the way, and the video we're going to watch after,
So the idea
but
then of
I just want to
perturbation
refresh my mind.
Is that the idea then is if H is equal to H naught plus lambda H prime, then I can think of the I can do a perturbation expansion. And I did this last time, so I'm going kind of fast right now. And I did a perturbation expansion. So what we did is we say, well, we can write the state that we want as a perturbation expansion. The perturbed state, I can write it as I have the lambda to the zeroth order term plus the first order term, lambda to the 1 plus the second order term, lambda squared plus the third order term, lambda cubed, etc. And I have I similarly have my perturbed eigenenergies. I have my zeroth order term, my first order term, second order term, etc. And so then then the whole point of perturbation theory is to find all these terms, find them. And so what we do is we want to find all these terms. We want to find psi n1, en1, psi n2, en2, etc. We usually stop at this. We usually don't go past 2. Don't go past 2. There are monsters there. Don't go past 2. We won't go past 2. Other people like theorists and people who are really into this do go past 2, but very few people do. There's only a few brave souls who will go past 2. And so then to find these terms, we simply solve the Schrodinger equation. It's very easy. You just say H, which is H naught plus lambda H prime times the wave function, which is psi n, is equal to En times psi n. That's the Schrodinger equation. But now what we do is we plug in these terms. We plug in the perturbation expansions, plug in the per expansion into this. And when you do that, then the next thing to do is you group the terms that have the same order. Group terms, we find some mess of stuff times lambda naught plus some mess of stuff times lambda to the 1 plus some mess of stuff times lambda to the 2 plus equals 0. And then we say that this can only be true if this equals 0 and this equals 0 and this equals 0, etc. And so this gives us our.
And this is just it's a thing from linear algebra. Because it's a linear combination. Because quantum mechanics exists as Hilbert space, all states exist as vectors that live in Hilbert space, and they're all mutually orthogonal to each other. Because of that, then that just means that, of course, all these states added together is going to be linearly independent. Okay, they're going to be a linear combination.
0th order equation. This gives us our first order equation. And this gives us our second order equation. And these are the equations of perturbation theory that we have to solve perturbation theory. And so let's write them down. The perturbation theory equations that we get from this treatment, they look like this. I wrote them down last time, so this is also a repeat. But it's still so important. So the 0th order equation looks like this. So I'll write it right here. The 0th order equation looks like this. Actually, I'm going to put it to the left. That space. The 0th order equation looks like this. H naught psi n naught equals E n naught psi n naught. That's what we get, and that you've seen that before, so that makes sense. And then the first order equation is less intuitive. It's not something you've seen before, unless you've taken this class before. H naught times psi n1 plus H prime psi n naught equals E n naught times psi n1 plus E n1 psi n naught, and that's it. I want you to notice that the superscript. This is a little trick that I find useful. The superscript adds to 0 for the 0th order equation, but the superscript adds to 1. Superscript adds to 1 for the first order equation. See, I have like 1 plus 0 equals 1, 1 plus 0. You can sort of see how the superscript adds to 1. And for the second order equation, the superscript adds to 2. So you can see a little pattern in the equations. Let's write the second order equation. H naught psi n2
2 plus H1 psi 1.
See, the superscript adds to 2
equals En naught psi n2 plus En1 psi n1.
1 plus
En
n2
psi n naught.
And you can see that the superscript adds to 2. Superscript goes to 2. Okay, so those are our 3 equations: 0th order, 1st order, 2nd order. And so now the trick is to solve those 3 equations. I hit the record button, didn't I? I did, yeah, I'm pretty sure I did.
It's recording.
Yeah, okay. It's like I did this.
Yeah, and then also, so this one has one, so you'll have 1 term, 2 terms, 3 terms. Is first order expansion, you have 1 more extra term. Second order expansion, you have 2
so now,
terms.
all right, so now that's fine. So now it's basically, what we want to do is solve these equations. So why do we want to solve them? What do we get out of it? why solve them? Well, the reason we want to solve them is because, look, let's look back here at our perturbation expansion. This was our initial assumption, right? And so let's do this, because we can set lambda. Lambda is a variable. I can set lambda to anything. So let's set lambda to, can you guess? Can somebody guess?
1.
One.
Yes. Let's set lambda equal to 1, because now if lambda is 1, all of these things equals 1. Lambda 1, lambda 0, they all equal 1, right? Now if those things all equal 1, then I can rewrite these perturbation expansion, and now the lambdas are gone. And what I have instead is I have psi n is equal to psi n naught plus psi n1 plus psi n2 plus dot dot dot, and I have en is equal to en naught plus en1 plus en2 plus dot 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 dot. And so we see that this is what we want. This is the eigenstate and the eigenenergy for the perturbed Hamiltonian. And so then the trick, then what we need to do is we must find these perturbation terms, because see, this is the one that we know already, the unperturbed. And so you can see that, for example, the eigenstate psi n is equal to the unperturbed state plus the first order perturbation plus the second order perturbation, and the same for the energy. The energy is equal to the perturbed energy plus the first order correction plus the second order correction. So we must find the corrections, what we call the corrections. And so in this class, what we will find is, this is what we will find. This is how far we will go. We will find en1, en2, and psi n1. So basically, we're going to cut this perturbation expansion off right here for the wave function, and for the energy, we're going to cut it off right here. So we're going to say, so what we're going to do in this class is we're going to say that the perturbed wave function is approximately equal, that's why the wiggly signs, is approximately equal to psi n naught plus psi n1. And we're going to say that the energy, the new eigenenergy is approximately the old eigenenergy plus the first order correction plus the second order correction. All right, that's as far as we're going to go. But I want you to know that we could go further, but it's just a lot of work, and it's usually not worth it. So this is basically like the main result of perturbation theory, is to sort of understand this. So now let's find these terms. So there's 3 terms that we have to find. Let's find the first one. Let's find the first order correction to the energy, en1. That's the first order energy correction. That's the language. That's how you say it. The first order correction to the energy due to the perturbation. This is like how much the perturbation changes the eigenenergy. Okay, so let's do that. Then let's find it. So we'll start with the first order equation, and let's go back and remember what it was. Here it is. It's this equation. Dun, 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 dun. We're going to use this equation, which we derived in class. And so let's use that equation. And so we'll take that equation, which is the first order equation, and what I'm going to do is I'm going to left multiply that equation by
we'll just watch it. I think so after watching these lectures, I think I'll go through all the homeworks, because there's only 3 homeworks to go through. So watch these lectures, go through the 3 homeworks, and then what else can I do?
This.
What else?
A bra. Boom, this one. I'm going to pick this bra, psi n naught, and I'm going to multiply that equation by this bra. And I can always do that, because if you do the same thing to both sides of an equation, that's allowed. So let's multiply the first equation by this bra. And when I do that, what we see is this. It's really nice. It's just, we get this equation. We can see that we get psi. I'm not going to write it there. I'm going to write it below. And I'm going to write it here. Psi n naught times h naught psi n1 plus psi n naught h prime psi n naught equal to psi n naught.
Okay. So I am going to write some stuff down. So 0th order is just h naught psi n naught is equal to e n naught psi n naught. First order would be h naught psi n1 is equal to plus h prime psi n naught is equal to e n naught psi n1 plus e n1 psi n naught. Yes. Second order, h naught psi n2 plus h prime psi n1 is going to be equal to e n naught psi n2 plus e n1 psi n1 plus en2 psi n naught, I think. Is that what it is? En naught psi n2, en1 psi n1, en2 psi n naught, h naught psi n2, h prime psi n1, h naught psi n1, h prime psi n naught, en naught psi n1, en1 psi n. Yeah, okay.
I think both sides is this. It's really nice.
And then for the first one,
we get psi. I'm not going to write it below.
psi n naught
psi n naught times h naught psi n1 plus psi n naught h prime psi n naught equal to psi n naught e n naught psi n first order correction plus psi n naught e n1 times psi n naught. Okay, a lot of writing for this stuff. Okay, so that's what we get. It's it's a lot of writing, but it's pretty straightforward. And let's see if we can simplify this a little bit. So if I here, I can simplify this because I noticed that h naught is a Hermitian operator, so it can operate to the left or to the right. And so when h naught hits psi n naught, what does it turn into? Somebody tell me.
En naught.
That's exactly right. So it turns into en naught, and that means that I can take it out. And so this term becomes en naught times psi n naught psi n1. Now there's nothing I can do to this term. This term is there's no elegant thing I can do to that term. So I'll just rewrite it. But this term I can do something to because that's a constant. En naught, so I can take them out. So this is equal to then en naught psi n naught psi n1. That's right. And then plus plus en1 psi n naught psi n naught. Okay, so what does this equal to? Psi n naught on psi naught, what is that?
It's 1, right?
Exactly. Yeah. That's 1. And notice how these two guys cancel. So these two guys cancel, yeah. And so then I have, so I'll just rewrite it. So then I have en1 is equal to this equation, psi n naught h prime psi n naught. Okay. And this is our major, this is like, I would say this is probably the most important result from perturbation theory. So, if you sort of forget everything about perturbation theory, just remember this, you'll be doing pretty good. Well, not for this class, but for 10 years from now. So this is really important. So this is why we love perturbation theory, because look, I could say the point is that this is an expectation value. It's an expectation value. It's easy. Expectation value is easy to calculate. Easy peasy, easy to calculate, because it's just equal to en1 is just equal to, it's just an integral, right? Psi n naught star of x h prime times psi n naught of x dx for a one-dimensional system, say from -infinity to infinity or whatever the boundaries are, depending on the details. But I just want you to see that this is easy to calculate. And so look what I've done. I mean, look at this. This is an amazing result, because basically I've just showed you that we've just solved this. H psi n is equal to en psi n, and I've just calculated en, the eigenstates. If h is equal to h naught plus h prime, some Hamiltonian that I have no idea how to solve. It's like way too hard. I don't know what tricks to use, but I don't have to do nothing. All I do is I just say, if someone says to me, what are the eigenenergies of this new Hamiltonian? All I do is I say, well, I know the other one. I know the unperturbed Hamiltonian. Those are easy. I just look them up in a book from undergraduate quantum mechanics. But then I just say, and then I'll just add on a little correction. And that's my new eigenstates. And I got to put wiggles there. It's approximate, but I hope you can see the power of that. It's like super simple. And then this is just an integral that I know how to do. It's an easy integral, because I just take the unperturbed states and I just find the expectation of the perturbation using the unperturbed state. So that's a very beautiful result, very powerful. But it is approximate. It just gives you a sense of the answer. It's approximate, but it works better than you might expect. So it works pretty good. So wow, okay, look, that's like a major breakthrough result. So let's keep going and let's see what other amazing things we can do. So let's find the wave function. Let's find the perturbed wave function psi n, and let's say that psi n is approximately equal to the unperturbed wave function plus the first order correction. So then let's find the first order correction. Okay, so
I was just thinking, what if I unplug my laptop? I'm gonna unplug my laptop, see how long this can go on for without wall power. So just straight from the battery. Let's see how long we can go for.
That's like a major breakthrough result. So let's keep going and let's see what other amazing things we can do. So let's find the wave function. Let's find the perturbed wave function psi n, and let's say that psi n is approximately equal to the unperturbed wave function plus the first order correction. So then let's find the first order correction. This is the second major result from perturbation theory. So to find that, what we're going to do is let's go back to the first order equation and let's rewrite it. Let's rewrite the first order equation for the perturbation equation that we derived. And so where is that equation? It's here somewhere. Yeah, there it is. Okay, that's our first order equation right there, little star. And so what I'm going to do is I'm going to rewrite it. I'm going to bring this guy over there, and I'm going to move this guy over there. I'm just going to rewrite that equation ever so slightly. So, and it's going to look like this. It's not hard. Just moving the terms around a little. H naught minus en naught times psi n1 is equal to negative h prime minus en1 times psi n naught. Okay, that's the first order equation. That might
Okay, so basically you're just writing things in terms of their states, and then you're factoring out these and applying the state to that, because you can do that. Because it's quantum mechanics, basically just linear algebra, E n naught prime minus h prime, psi n naught.
It might look a little weird. You've never seen that equation before. But it's not a hard equation.
Yeah.
We can write it down, and it's it's not too hard. And so we're gonna do a trick. We're gonna do a trick. We're gonna write.
I'm gonna go for another cup of tea because I like tea. I'm going to go for another cup of tea because I like tea. I love tea. Okay. I love tea so much you'll never believe how much I love tea. Yeah, that's right. I'm mobile. Yeah, that's right. We can vlog. What's up, guys? Welcome to my live stream. What's going on? What's popping? It's live stream time, baby. We're live streaming. I'm here in my crib. Here in my crib. Here in my garage. Here in my garage. It's bright outside, guys. I don't think you realize how bright it is outside. Beautiful. It's beautiful weather for sitting inside all day. It's quite gorgeous. It's gorgeous outside today. It just makes me want to sit inside. Makes me want to sit. Ooh. Ooh, yeah, baby. I know I'm going to get tired, so instead of recycling the tea bag, actually, I'm going to get another. Jesus. Dude, my throat has been so messed up. Every single time if I ask a question in class, it's like, excuse me. Like, it's like that, man. Yeah, it's hot enough. It's so bad, man. My throat is so bad. Like, I don't sound sick if I'm just talking normally, but a lot of phlegm will build up, man. You'd never believe it. Look at that. This time I'm an expert. This time it's... The thing is still on. Why are you so high up, bro? Eyes down here. Not that down, but there we go. Teabag it up. Teabag it up. I feel like a lot of my water just spilled, dude. I feel like this cup was a lot more filled with water, but whatever the case might be, it is what it is.
That's the trick. So we know that psi n naught is a complete basis. We know that because it's the solution of this equation. H naught times psi n naught is equal to E n naught times psi n naught. And so this is a Hermitian operator. And so we know that the eigenstates are form a complete basis, and that's something you learned last semester. Okay, and so that means then that I can write the thing we want. The thing that we want is psi n1, the first order question. Mm-hmm. So this is a trick I'm going to do. Check this out. I'm going to write it as an expansion in the unperturbed basis, the basis that we know. So since this is a complete basis, I can always write anything in terms of that basis. So I'll take the thing I want and I'll write it as an expansion in this complete basis. But that means I have to put in these coefficients c, m, n. Okay, and so this is the thing we want, and I've rewritten it in terms of the basis that we know. But now, because I've rewritten the problem, now the thing that we want, the new thing that we want is these coefficients c, m, n. Because if we know the coefficient, then we know psi n1 because it's written in terms of those coefficients times things we already know. So the thing we know, this is the thing that we need to find. Those coefficients must find, because once we find those, then we know psi n1. Okay, so that's the whole point. So let's find these coefficients, and so But before we do that, let's think for a second. So we're about to write a bunch of equations, giant equations. But before we do the equations, let's think for a moment, and let's think about Hilbert space.
You hear what he said? That he said before we do the equations, because we're about to do a whole bunch of equations. But before we do that, let's think for a moment. Oh, I love that, bro. Oh, if my professor now did that shit, god damn.
Hilbert space, where everything's possible. I love Hilbert space. Okay, so you can find whatever you want in Hilbert space. And so let's consider Hilbert space. And so in Hilbert space, we think of these states. Remember, these states are all vectors in Hilbert space. States are vectors in Hilbert space. And so that means that I can think of the state that I want, psi n, is equal to, it's approximately equal to the state that I already know plus some first order correction, right? Okay, now think of these as vectors. And so check it out. This is a funny thing. It's really obvious when someone points it out to you, but it's sort of for fun. Okay, so here's my unperturbed vector, this guy. He is a vector in Hilbert space. Let's draw him. This is what he looks like. He looks like a vector. And psi. Okay, now I'm gonna ask you a question. What is his length? Somebody tell me.
It's 1.
Is it the inner product with itself?
Yes, that's correct. What is it? Do that calculation in your head and tell me the answer.
1.
Yes, it's normalized. The length is 1. Length equals 1 because it's normalized. Such a simple thing. Of course, the length is 1. It's normalized. But then it makes a sort of a profound thing, because then we ask ourselves, what does h prime do to this vector? What is effect of h prime? And I'm asking you, this is a very meaningful question, because remember, I've told you that the whole point of perturbation theory is you have to think of your unperturbed states and your vectors in Hilbert space, and then you slowly turn on that perturbation, and then your unperturbed states morph. They change.
Oh wait, yo, check this out. I can make it seem like I'm a student in there. Oh, hold on. Watch this. Can I duplicate? Oh, I can. Okay, watch this. Hell yeah, now it looks like I'm just a student there. Yeah, I'm just in the Zoom meeting. Why is it so bright, bro? What the frick? Everything's now just really overexposed. Okay, there we go. Yeah.
Asking you the question right now.
Okay, that's cool. Okay.
What happens to the Hilbert state? How does it change in Hilbert space?
Because it's built up with the energy.
Well, I'm not talking about energy. I'm talking about the state. The state
I don't care. You can just pretend like I'm in the class.
Well, that's a good comment. So let's in Hilbert space.
You could build up with the energy.
Well, I'm not talking about energy. I'm talking about the state.
Wait, what? What is the effect of h
The state is a
prime?
vector. There is an energy associated with it. That's correct.
H prime is just a rotation
Well,
vector.
that's a good.
It's a
comment. So let's
rotation.
think about that for a second.
It's a rotation matrix. It'll rotate that state in
Hilbert
Hilbert space by some amount.
Somebody answer that question.
It's a rotation.
So basically, I'm asking, can the length change?
No.
Why not?
Because it's
Because
normalized.
probability always has to be 1.
Yes.
Yeah.
The length of the wave vector has to be 1 in Hilbert space. Otherwise, quantum mechanics makes no sense, because the whole point of quantum mechanics is probability, and the probability has to be 1. It has to be normalized, because something's got to happen. And so, if you don't normalize probability, quantum mechanics falls apart, and quantum mechanics loses meaning. So I'm emphasizing that because it's a really profound thing. It's a really big deal. That the length has to be constant. Okay, so let's go back to that question. So what is the action of h prime on the unperturbed state? What's it do to it?
Rotates it.
Yes, that's exactly right. It rotates it in Hilbert space. The length cannot change. It rotates. So that's really profound. So that means that the new state is like this. And I didn't draw my circle well, but the idea is that the length doesn't change. And so this then is psi n. The perturbed state is the old state, but the way to think about it is that the perturbation rotates the state in Hilbert space. And so what is this little vector that connects? What is this little vector that connects the old state and the new state? What is that little vector? What is he?
Psi n1.
Yes, that's exactly right. Psi n1. That's right. So from this very simple, you have a question?
Yeah, so just a small question then. Would rotating it be, maybe I'm just thinking about this a little wrong, but would it also be like giving it a phase?
Giving it a what?
A phase factor?
A phase factor. No, I don't think so, because look, it's just linear algebra. It's like x, y, z. I mean, if I have a vector that's pointing in the x direction, if I hit it by phase factor, does it suddenly point in the y direction? The answer is no. You see what I'm saying? It's just linear algebra. So the beauty of this, that's the beauty of quantum mechanics and linear algebra, is all your intuition from linear algebra you just can bring into quantum mechanics. So every question you ask about Hilbert space, you can answer just by using your intuition of linear algebra.
Yeah, because the phase, that phase factor he's talking about, that would be on the wave function itself, I'm pretty sure. Jesus Christ, man. Yeah, that phase factor would be on the wave function itself. Like, you can think of the wave function as just like a wave. And then if you have some phase factor, you're going to like, instead of doing it like this, it'll be like, imagine this is the cutoff point. Instead of being like that, it'll be like, it'll be like that. Whatever. You know what a phase is, bro. Don't even. Don't pretend like you
but now
don't know
there's
what a phase
concepts
is.
from this very simple geometrical picture, which is that there's a couple of things.
Can you
Two
not
things.
be overexposed,
Thing.
please?
The first
Thank
thing
you.
is that I see that there's a relationship between. I'll say this. Let's see. Let's make this more sensible. The first thing is that there's a relationship between the vector psi n naught and the vector psi n1. There's a geometrical relationship between them. What is that geometrical relationship? Somebody tell me.
They're orthogonal.
Yes, they are orthogonal, exactly. Now, if my perturbed state rotated a lot in Hilbert space, they sort of wouldn't be orthogonal, but for little rotation, they're orthogonal. And that's why, it's perturbation theory, everything's small. Exactly, they're orthogonal. You can just see it from the picture. And there's another thing, which is that, there's something about psi n. The point is that, actually, the second point is really just an elaboration of the first point. The second point is simply that the first order perturbation, because it's orthogonal to psi n naught, it's not really two things, it's really just one thing, I should say. Let me just change this, it's just one thing, but I just want to say it in one thing, said in two different ways. That means, because these two guys are orthogonal, then psi n1 has no component of psi n naught. It's orthogonal, and so it's kind of a trivial statement, but it has important implications. So there's no component of psi n naught in psi n1. Can you see that? It's just, you get it just from this very trivial construction. It's a very profound and important point. I think it's cool that you can just see it from this very simple geometrical construction. Okay, so let's now continue with the math. So now that we've done this geometry, let's go back and let's remember that now we've written psi n1, the first order correction, in terms of the unperturbed states. And so what I'm going to do then is I'm going to plug that in, because I'm going to plug this into this first order correction. So plug in. Okay, that's a term. Okay, so we want to plug in. Okay, so we're going to plug it in. And so when we plug it in, it looks like this. So what we're going to get then is plug in. Okay, so we're going to plug it in. And so when we plug it in, it looks like this. So what we're going to get then is H naught minus E n naught. Now it was multiplied by psi n1, but now I'm going to replace psi n1 with this sum, C m n. And this is a sum over m. Psi n naught is equal to minus H prime minus E n1 times psi n naught. Okay, that's what I have. But look, psi n1 has no component of psi n naught. And so when I do this sum over m, one component there is missing. What component is missing?
Psi n naught component.
That's right. M cannot equal n. And that's important. So that means that when I do this, I have this sum, psi n over m, psi n naught is equal to minus H prime minus E n1 times psi n naught. Okay, that's what I have. But look, psi n1 has no component of psi n naught. And so when I do this sum over m, one component there is missing. What component is missing?
Psi n naught component.
That's right. M cannot equal n. And that's important. So that means that when I do this, I have this sum, psi n1 equals this sum here, but in this sum, m does not equal n. So I'm summing over all the other states, but there's no component of n. And the reason for that is because otherwise it would change the length. So I'm summing over all the other states, but there's no component of n. And the reason for that is because otherwise it would change the length.
Oh.
See what I'm saying? So it's from that tricky geometrical argument. So hopefully that you can see that. Professor. Yeah.
So we made this argument that H prime has to rotate the vector because the
That makes sense.
But why can't I make that same argument for say H?
That makes sense. That you can't have. Okay, you can't have a component. I don't get where the psi n1 is coming from this, but I understand that you can't have the m and the n. You can't have them having one component in another. So I guess you just eliminate. I don't get how
because,
that
I know that H naught has to scale the vector because it's
eliminates the component.
What argument? I'm sorry. Make what argument for H naught?
So we said that the H prime, the perturbation, has to rotate the vector in Hilbert space.
Yeah.
Because it's it's a normalizing probability vector some point.
Yeah.
But I know that H naught times that vector is scaling it by energy because it's an eigenstate.
Wait, H naught times what?
Phi n naught.
Okay. Yeah.
H naught. Yeah, but why can't I make the same argument that I can't scale the length because it's normalized?
No, it's not. It's not. Look, I mean, when I say H naught hits psi n naught, it equals E n naught times psi n naught. So in the language of linear algebra, we say that psi n naught is unchanged because it hasn't been. It's the same vector in the language of linear algebra. And so yeah, I mean, the psi n naughts are just. I mean, the way to think about them, they're just the psi n naughts are just the basis state. They're just like an orthonormal basis that's sitting in Hilbert space, and so that's the way to think about it. And so if I hit that orthonormal basis, it's not being changed. It's like I'm not. The thing is the whole point is that if I have some matrix, H times psi is equal to, I don't know, gamma psi prime. Typically if I have an operator or matrix that hits a vector, typically that vector will turn into, there's some constant, but then this vector psi prime is pointing in a different direction, and if that vector psi prime is pointing in a different direction, then that vector is not an eigenstate. It's not an eigenstate of H. And so the point is that the point is that all the aperture vectors are eigenstates, and so they don't rotate, they don't change.
Okay, yeah, I see now. Those are just
I guess I was having questions on this too. I guess if you look at psi n naught, I guess I was thinking about it as a unit vector, and the constant en0, it would be like a constant times that unit vector. So I guess it was scaling, but I still don't understand why it just rotates. Maybe it's just like a characteristic of Hilbert space.
Okay, but look, I think that let's go back to this picture. It goes back to this picture from the very beginning. The thing is that I have a set of states of H naught. Oops. I have a set of states of H naught. Here they are, okay? Those states are vectors in Hilbert space. The whole point of perturbation theory is to find a new set of vectors in Hilbert space, which are the eigenstates of this operator. And the eigenstates of this operator H, those eigenstates are these guys. And the whole point is that when I turn on the perturbation H prime, the old states morph into the new states. And the way they morph, it's a rotation. They go into the new guys. So I go, here are the old guys, I go, and now they are the new guys. They rotate it. And that rotation is what we're talking about. Because as I turn on H prime, the eigenstates that used to be eigenstates of H naught are now become eigenstates of H prime. And of course they gotta be normalized. They gotta stay normalized. That's sort of almost like a given, a constraint. They always are normalized. And so they gotta rotate. Okay, well I guess that's as far I guess as I can take it now. You can talk to me or Newton further about that. Okay, so we have to solve this equation. And so the critical thing is that the new eigenstate, the critical thing is because of this rotation property, the psi n1 cannot have a component of psi n naught, and that's really important. So if it's not making sense today, right now, think about it at home, and until that makes sense. And if it doesn't make sense, you should talk more to me or to Newton. Okay, so let's see. Let's continue with this. Where are we? Okay, so we have to solve this equation here, and so we're gonna do a trick. We're gonna do a math trick, and the math trick is to left multiply by the bra psi p naught. Where p is arbitrary. And so I'm just going to do that to both sides of the equation. So it's just a math trick, but I can do it. I can hit both sides with the same thing. And so when I do that, then I'm going to bring it. I can rewrite it. And so let's see how I want to rewrite it. I think I'll rewrite it like this. I can bring the summation out. So it's m not equal to n, and I have c m n, and I have psi p naught h naught minus en naught psi m naught is equal to negative psi p naught on the left, h prime minus en1 inside, psi n naught on the right. Okay, so I just left multiplied and pulled the summation out. And now what I can do is this guy, when this guy hits this guy, what is he going to turn into? Somebody tell me.
Em naught.
That's exactly right. He'll turn into em naught. And so that's quite useful. And so then so I can then rewrite this like this: m not equal to n, c m n, and I can pull these guys out because they're constants. Em naught minus en naught times this guy, psi p naught psi m naught is equal to, and now this one, I can break it into two pieces like this using just some simple associative property, psi p naught h prime psi n naught plus, and because that's a constant, I can bring him out, en1 times psi p naught psi n naught. Okay, so it's just a lot of tedious equations, but it's pretty straightforward. The math I think is straightforward. And so this is for any p. So let's break it up to two cases. There are two cases for p. One of the cases is, well, I'll just do it. One is p equals n, and the second case is p does not equal n. And you might be getting lost in all the notations. Remember, you just have to remember what we're solving for. Remember, the whole point is we're solving for psi n1. We're looking for the first order correction to the nth state. So n is fixed in all of this. N is the one thing that's fixed. M is an index and p is an index. So n is fixed. P and m not fixed, because those are the variables that we are summing over, or are arbitrary. Okay, so I just want you to kind of remember that. And so let's do the first case, where p is index is equal to n. And then for this case, let's look at this equation, because we have this equation. This is our equation that we got. And so we want to look at this equation for the two cases. And so for the first case, if p is equal to n, then let's take a look at this, because if p is equal to n, then what happens is we have this. Look at this for the left side. Then we have psi n naught, psi m naught on the left side. You see that on the left side? So what is this equal to?
0.
Why is it 0? Why couldn't it be 1?
M isn't equal to n.
Exactly. That's exactly right. So that's a little tricky. I think that's right. You nailed it. Left side. And so and then on the right side, if I plug in p equals n, then I have on the right side.
Wait, m cannot be equal to n So then you'll have psi n. If p is equal to n, then psi n, psi m will be equal to 0. So then what that does is it gets rid of all these extra whatever factors. And now on the right, you're just left with en1. What? So what is this doing?
Then you can see that here that I have psi n naught, psi n naught. And what's that equal to? Psi n naught on psi n naught.
Just 1.
That's right. And so the equation becomes really simple. I just end up with en1 is equal to psi n naught, h prime psi n naught. Okay, so that's what I end up with. And that's pretty boring because we already knew that. We already solved for that last time. All right, so we already got that one. So we already know that. It's nice, that's true, but that's just the first order correction to the energy. We already knew that. So let's do the more interesting case where p is not equal to n. And so when p is not equal to n, now if I look at the left side, I have this. I have psi n naught. I'm sorry, let's get this right. On the left side, I have psi p naught, psi m naught. And p does not equal n. And so what does this equal?
Would it be the coefficient?
No, remember these are normalized.
It might be 1.
It might be 1, but it might be what?
0.
0.
Kronecker delta.
Right? Because these are orthonormal vectors. And so when is it 1? When p is equal to?
P.
Yeah.
Exactly. And then, so it's a delta. Look, it's a Kronecker delta. It's going to be delta. That's what like this delta.
P.
It's a Kronecker delta. And of course, and we also know that on the right-hand side, on the right side, we're going to have psi p naught, psi n naught. And what is this going to be equal to on the right side?
0.
Exactly, because p is never equal to n. And so now our big complicated equation, now, and so now on the, since that's a Kronecker delta, then I have this. I have the sum over m not equal to n, c m n, Kronecker delta, p m times e m naught minus e n naught is equal to negative psi p naught h prime n naught. Okay, that's our equation. But because I have a Kronecker delta, this collapses the sum. It collapses m because now m has to go to what in the sum? This is the trick of Kronecker deltas. What does m have to go to? The sum collapses, m goes to what? Yes, m goes to p. That's a math trick. So then the left-hand side becomes c p n times e m naught minus e n naught is equal to negative psi p. P collapses, m goes to what? Yes, m goes to p. That's a math trick. So then the left-hand side becomes c p n times e m naught minus e n naught is equal to negative psi p h prime psi n naught. And this is very cool because now we have it. You just check it out.
The EM naught should be an EP naught as well.
Oh yeah. Thanks. Okay, so now we have it. C p n is equal to negative psi p h prime psi n over e p naught minus e n naught. Okay, this is a big result. That's the coefficient that we wanted. We got it. So this gets 2 stars. That's really important because now let's go back. Oh my God, how far back do I have to go? Okay. Yeah. Okay. So remember, this is what we wanted all along. Is this guy right here? So there he is. So let's go back here. And so remember, we wanted psi n1 is equal to the sum m not equal to n c m n psi m naught. And so now we have it because we have this coefficient. So let's just turn the p into an m. We can do that because it's just a dummy variable. And so then we have that this thing is equal to then we have that psi n1 is equal to the summation m not equal to n of it's just a dummy variable.
What just happened?
Okay, that's a big
what just
result.
happened?
That's the coefficient that we wanted. We got it. So this gets 2 stars. That's really important because now let's go back.
Psi n1.
Oh my God, how far back do I have to go? Okay. Yeah. Okay. So remember, this is what we wanted all along. Is this guy right here? So there he is. So let's go back here. And so remember, we wanted psi n1 is equal to the sum m not equal to n c m n psi m naught. And so now we have it because we have this coefficient. So let's just turn the p into an m. We can do that because it's just a dummy variable. And so then we have that this thing is equal to then we have that psi n1 is equal to the summation m not equal to n of okay, good. Yeah, that's going to be the sum of psi m naught h prime psi n naught. Here it'll be e n naught minus e m naught. So the negative sign, I switched the order on the denominator. So the negative sign went away, and then this becomes 1 times psi m naught. Okay, and so this is our result.
And Professor, just to be clear, n goes from 0 to
M basically M is summing over all the eigenstates, and so it depends. It sort of depends on the details, of your problem. Like you might have, it depends, it might have a restricted subspace where it's not infinity. It just depends on the details of your problem. But basically, you have the unperturbed Hamiltonian, and it's just summing over all the eigenstates of the unperturbed Hamiltonian, whatever they are. Is that okay?
Okay.
Does that answer your question? So we can say yes. I can say that M equals 0 to infinity, but does not equal n. So that's fine. Although it sort of depends on the details. Okay. And so what I want to do is we'll do an example. But first, let's just think about the intuition for a second. What is the intuition? Like, what does this mean? Because the thing is that when you look at this equation for the first time and you've never seen it before, it looks really weird to you and not very intuitive. But I want to point out that this is like the second major result from perturbation theory, and this result is sort of like you can think of it as a rewriting of the Schrodinger equation. And remember, I told you that perturbation theory creates a new quantum mechanics intuition, and so now I want to start talking about that new intuition. And so when you look at this equation for the first time, it doesn't mean anything to you because it's just the result of some long string of calculations. But I want it to start making sense to you physically, and it actually means something. And so let's talk about the intuition. So this is the way to think about it. This is telling me that because before, remember, we start with psi n naught, which is an eigenstate of h naught, and then the question is, how does, and then we know then that psi n is equal to the old state psi n naught plus the correction. And so then the question is, what is this correction? How do we think about it? And this is the correction. We just calculated it. But what does it mean? What's the meaning of it? And so before the correction occurred, the eigenstate was an eigenstate of the old Hamiltonian psi n naught. And so before, and when I say before, I mean before turning on the perturbation, I had h naught and I had all of my states, all my eigenstates, boom, 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 boom. They're all there. And now one of them is the nth state, and this is the n plus 1, n plus 2, n plus 3. This is the n minus 1, n minus 2, n minus 3. Da, da, da. These are all my eigenstates of h naught. Now, and this one this corresponds to psi n naught. Now, what's happening is that this state morphs into this new state, which is the eigenstate of the Hamiltonian h, which is equal to h naught plus h prime. And so this new state is psi n. Okay, what is this equation telling us? This result. What this result is telling us is that
Back it up.
which is an eigenstate of h naught. And then the question is, how does, and then we know then that psi n is equal to the old state psi n naught plus the correction. And so then the question is, what is this correction? How do we think about it? And this is the correction. We just calculated it. But what does it mean? What's the meaning of it? And so before the correction occurred, the eigenstate was an eigenstate of the old Hamiltonian psi n naught. And so before, and when I say before, I mean before turning on the perturbation, I had h naught and I had all of my states, all my eigenstates, boom, 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 boom. They're all there. And now one of them is the nth state, and this is the n plus 1, n plus 2, n plus 3. This is the n minus 1, n minus 2, n minus 3. Da, da, da. These are all my eigenstates of h naught. Now, and this one this corresponds to psi n naught. Now, what's happening is that this state morphs into this new state, which is the eigenstate of the Hamiltonian h, which is equal to h naught plus h prime. And so this new state is psi n. Okay, what is this equation telling us? This result. What this result is telling us is that first, I want you to appreciate that before I turn on the perturbation, all of these eigenstates are orthogonal. All the psi naughts are orthogonal. They have one eigenstate has no component of the other component in it. They're orthogonal. But now what's happening is, look at this new equation that we derived. It's saying that the correction is bringing in all the other eigenstates. There they are. They're all there. It's adding all the old eigenstates to the one that we picked. So it's basically saying that the way that this state rotates in Hilbert space and morphs into the new state is that it gets a little piece of all these other guys. They get added to it. Do you see that? All the guys on top and all the guys on bottom. They all are getting added to it. So this is what the word you might use is a mixing. They get mixed in. So all the eigenstates start getting mixed in. They start getting added to the old eigenstate to create the new eigenstate. You see that? And so then the question is, how much mixing? How much mixing? How much does each of those states get mixed into the old state? Well, the amount of mixing is this. It's psi m naught h prime psi n naught divided by e n naught minus e m naught. That's how much mixing. The answer is this. It's this coefficient that we just derived, this CMN coefficient. That's how much mixing. And so what is the intuition that we get from this? Well, first, the simplest intuition is in energy. Energy. If m if em is far from en, if em naught is far from en naught, then do the states get mixed much? Yes or no? Somebody tell me the answer.
No.
Why not?
The denominator is greater, or
yes, exactly. That's exactly right. The denominator gets big, so the mixing is less. If em naught is far from em, then less mixing. But the converse is true as well. I mean, if the energies are close, then do they mix a lot?
Yeah, that's true as well.
They mix like crazy, all right? And in fact, if they're the same in energy, then we get a divergence. So we'll talk about that later. But I just want you to get some intuition. The bottom line is states that are close in energy mix. If I have a perturbation, they mix like crazy. Whereas states that are far away in energy don't mix.
Kind of
so
like
much.
magnets.
That's important. That's quantum mechanics intuition.
It's kind of like
another
magnets.
thing is in terms of the effect of the
We don't
perturbation.
attract that much. Ooh, they start attracting a lot.
We think of this as a matrix
Dude, putting me in like the Zoom thing is like
this
so
numerator is a
fucking
matrix
weird.
element. That's the technical term for it in quantum mechanics. This matrix element, I'll call it H prime M N. That's a matrix element from the definitions that you learned last semester.
How did he what?
Far away in energy don't mix so much. And that's important. That's quantum mechanics intuition. Another thing is in terms of the effect of the perturbation. We think of this as the matrix element. This numerator is a matrix element. That's the technical term for it in quantum mechanics. This matrix element, I call it H prime M N. That's a matrix element from the definitions that you learned last semester. So the numerator, basically the numerator of this fraction is the matrix element of H prime that connects the states M and N. And so if matrix element is small, then if the matrix element is small that connects the state M to the state N, then is there much mixing? Then does that state get mixed into the new eigenstate?
No.
That's right. If the matrix element is small, then less mixing. Because the question, the point is that this is telling me how much the nth state, the M, that state is getting mixed into the nth state. And so if that matrix element is small, then the mixing is less. So for the state psi M naught to mix with psi N naught, then they need to be connected by H prime. And the amount, the strength of connection is equal to this matrix element, psi M naught H prime psi N naught. And that's kind of intuitive, because it's sort of like, well, you know, psi M naught and psi N naught would not be connected at all because they're orthogonal. And if I turn on H prime, then that connects them. So how much does it connect them? Well, let's just see. If I hit one of them with H prime and then project it over on the other one, that tells me how much the H prime connects them. So that's an intuition that I want you to take away from it. You know, connected is equal to this matrix element, psi M naught H prime psi N naught. And that's kind of intuitive, because it's sort of like, well, you know, psi M naught and psi N naught would not be connected at all because they're orthogonal. And if I turn on H prime, then that connects them. So how much does it connect them? Well, let's just see. If I hit one of them with H prime and then project it over on the other one, that tells me how much the H prime connects them. So that's an intuition that I want you to take away from this, is that intuition. So now let's, okay, so and I just want to say that's a new intuition for you guys, but that's an intuition that everybody who uses quantum mechanics has that intuition. And that intuition is really important because it's easy. And we like easy things. Okay, so let's do an example. And the example is, suppose that we have, suppose I give you this, you know, H is equal to this. I have a square box, but half of it from x equals 0 to L over 2, it's normal, but from L over 2 to L, I give this weird potential. And this weird potential is going to be, this potential, actually, let's do this. Let's not call it H, I'll call it V. Let me give you some weird potential, V. It's an infinite square well, but here, I gave it this little weird part, alpha times x minus L over 2 cubed. Okay? That's the potential that I'm giving you. And I'm going to ask you, then I'm asking you, what are the eigenstates and eigenenergies? Basically, I'm going to ask you guys to tell me all the eigenstates and eigenenergies. I'm basically saying solve the Schrodinger equation. Solve it. Okay, I'm asking you to solve the Schrodinger equation. Tell me all the allowed energies and all the allowed eigenstates. What are they? Now, so the first thing you should do when you're hit with a problem like this is you go back to last semester and you say, okay, you look up in the book and you say, can I find this in the book? Is this a simple harmonic oscillator? Is it a particle in a box? Is it the Coulomb problem? Is it one of the ones that I know? And when you look at it, obviously it's not, okay? Because I put this weird asymmetrical cubic potential in there. The bottom line is there's no way you can solve this. This is too hard. It's impossible to solve. Now you can numerically solve it on a computer, but that's sort of cheating, you know. So let's not worry about numerical solving. But if I just say solve this, there's just no way to solve it. It's just too hard. So you would be stuck. You'd be like, I don't know what to do. I'm lost. But it turns out that you can just use perturbation theory, because what we can do is we can say, using perturbation theory, it's really easy, because we can just say, let's do perturbation theory. And using perturbation theory, we say H equals H naught plus H prime. And so I'll ask you, what is H naught? So somebody tell me, what is H naught?
0.
What?
0?
No, it's something familiar.
Okay.
H naught is the familiar potential. Remember, I want to say that the Hamiltonian that I gave you, the hard Hamiltonian, is something known plus something unknown. What's the known thing?
The particle.
Negative h bar squared over 2m times
Yeah,
d over dx squared. Yeah.
Yeah, you don't have to say it all. It's a square well, right? It's the infinite square well plus kinetic energy. Yeah, that's the familiar Hamiltonian, right? Is this okay? That's okay. So that's the familiar Hamiltonian, but that means that H prime is what?
The cubic function?
Exactly. It's going to be the alpha x minus L over 2 cubed. So in the language perturbation theory, I have the known part that completely know, and I have the unknown part. And now when I break it up, now I can. So now I'm good. Now I'm good to go because now we can solve it, because we know that we know that the known functions. So the known functions are the solution of this. And so we can we know the solutions. I'll just write down the answer. You know these guys. It's psi n naught of x is equal to square root of 2 over L sine n pi x over L. Right? Did I get that right? Yeah. And then you know that the energies of those guys, n naught is equal to n squared pi squared h bar squared
over
L squared.
2L.
Okay,
yeah.
so these are formulas that you all know, or if you don't remember them, you could every one of you could derive this. In the screwing around for like 10 minutes or whatever. So we all know that. Okay, so now that we know that, let's use perturbation theory, and we'll say that that the eigenenergies En is equal to the old eigenenergies plus the first order correction, and we'll say that the new eigenstates psi n is equal to the old eigenstate psi n naught plus the first order correction. So this is first order perturbation theory. We're using first order perturbation theory. And so let's just do it. So that means that we have to find these two guys. So let's find them. So En1 is equal to, it's really easy. We know the formula. It's going to be psi n naught h prime psi n naught, and that's just going to be an integral of psi n naught, which is going to be square root of 2 over L sine n pi L over n pi x over L times the perturbation. And so this is where I'll stick my alpha x minus L over 2 cubed times square root of 2 over L sine n pi x over L dx. And what are the limits of integration? What are the limits of integration?
0 to L.
L over 2 to L.
Yeah, well, what is the perturbation in this region of the box? It's equal to what?
0.
It's 0. So the integral is 0 in that region of the box. So what are the limits again?
L over 2 to L.
Yes. I just want you to see that. So it's important. You got to get these limits right, or you won't get the right answer. Great. So you just do that integral. Boom, you got it. I'm not going to do the integral. But just the final thing I want to do. I know I'm going over a couple minutes, but I burned up a couple minutes at the beginning with my technical failure. But let's just do that. Let's just quickly do the just to finish this up. Let's just do the other thing. Let's now calculate the wave function, the first order correction to the wave function for this problem. And so I'm going to use my basically what I want to say is, yeah, we know that psi n naught is equal to, we know that psi n is equal to psi n naught plus psi n1, and so we know that psi n1 is equal to this sum, and now I'm going to have the sum be of L, and you'll see why in a minute. L is a sum over L, not equal to n of psi L naught h prime psi n naught over the n naught minus the L naught times psi L naught. And so now we just got to plug it all in. And so I see that this is going to be, when I do all this, then it's going to be psi 1 sub n of x is going to be equal to, now I got to do this giant thing. So it's going to be a sum from L over all L. And now we just got to write it all out. It's going to be this thing. It's going to be the integral from L over 2 to L of this top part, which is going to be square root of 2 over L sine L pi, L pi x over L times alpha times x minus L over 2 cubed. And here I'm going to have square root of 2 over L sine n pi x over L dx. And then here, this is going to be sitting on top of the formulas E n naught, which is n squared pi squared h bar squared over 2m L squared minus E L naught, which is going to be L squared pi squared h bar squared over 2m L squared. And the whole thing is going to be times this guy psi L naught, which is going to be square root of 2 over L sine L pi x over L. And that is it. And that's the answer. So that's my eigenstate. So we did it. We got the eigenstate. We solved the Schrodinger equation approximately for this very hard perturbation. So that shows the power of perturbation theory. Okay, so that's all for now. Okay, see you later.
Thanks, Professor.
Oh yeah, you have okay. Somebody has a question.
Okay. That makes sense. Okay. So that's perturbation theory. That's that. Now we'll move on to, that's non-degenerate, and now we're going to move on to degenerate perturbation theory.
Share screen, iPad, little mirror trick. Okay, you guys can see the screen okay? It says second order perturbation theory, yeah?
Yep.
Okay, so it's time to start. So the plan for today is to discuss these two topics, second order perturbation theory and degenerate perturbation theory. Two very nice topics, very related, and so let's just dive into it. So sort of to set the stage, so far what we have is we have a situation where we have an unknown Hamiltonian, which is equal to a Hamiltonian that we know, plus some perturbation that we don't know, and which confuses us. And so what we want is to solve this problem, the Schrodinger equation. We want this.
Give me a bit. Oh my god. Oh, I'm tired, man. Jesus Christ. I drank 2 cups of tea as well, and I'm still tired. Oh my god. Bro, okay, so we're gonna watch this video, go through all the homeworks, and then that's it. And then we're done. It's 3:30 right now. This video will take 45 more minutes. So let's estimate we'll be done around 5. And then we have from like 5 till 9. So 6, 7, 8, 9. We have like 4 hours after that to do homeworks. Bro, you guys are with me for a while right now, okay? Because if I turn off the stream, I will have nothing in my mind to keep me accountable. And so I will do a whole bunch of garbage. So, yeah. Mm-hmm. Jesus. Okay, I'm gonna go. I want to take a break real quick. I'll be back. Whoosh. I'll be back soon. Give me a gosh darn minute, everybody. I have returned. Indeed. Yes, indeed. Can the exposure go down, please? Can the exposure be normal? Or is the... It's just gonna be overexposed, okay? The Logitech C920 cannot handle this. Okay, it can't. But anyway.
Plus some perturbation that we don't know. And
Now we're going into second order degenerate perturbation theory. Second order perturbation theory and degenerate perturbation theory. That's what we're going into. So probably looking at the second order approximation of energy, EN2. Because last time we did EN1, psi N1, and now we're doing EN2.
which confuses us. And so what we want is to solve this problem, the Schrödinger equation. We want this, and we want to know what are these eigenenergies and eigenstates. That's what we want. And what we know is we have the unperturbed Hamiltonian and the unperturbed eigenstates. Okay, so that's what we know. And so then what we do is it's really hard to find those perturbed eigenstates, but we use perturbation theory. And so perturbation theory gives us a way to move forward very easily. It's like the most useful trick in all of quantum mechanics. And so what we've done so far is we found that using first order perturbation theory, what we've done so far, we see that the unknown eigenenergy is approximately equal to the known
I
unperturbed
hope
eigenenergy.
with non-degenerate perturbation theory, we just have to do some like derivation. Derive this. Derive the terms for that. I would love that. That would be so dope.
The first order perturbation.
Because I'm ready for that. I'm ready to derive the terms.
Perturbation is very easy to find. It's simply the expectation value of the perturbation using the unperturbed state. And it's as simple. It's an integral. It's easy, and relatively easy integral. That's a lot easier to find than to solve the Schrödinger equation. And we also have shown so far that the perturbed eigenstate is approximately equal to the unperturbed eigenstate plus a first order correction. Where that first order correction, we calculated it, is equal to this weird formula.
Summation.
Which is not so weird when you think about it.
At
least it can give you some intuition that I described last time.
H prime psi n 0 over En naught minus Em 0 times the psi
n 0. It's a sum over all the states except for the end state. We're talking about the end state, and so the end state is determined is set by that. That's the end state. The one we're talking
contribution
about.
of all these other states
except for the end state, and that's it. Okay, so that's the first order results. But it turns out that we can get a more accurate expression if we go to second order. And the way to think about it is that in a perturbation expansion, the idea is that the eigenenergy is equal to the unperturbed eigenenergy plus the first order correction plus the second order correction plus the third order correction, etc. And the same goes for the eigenstate, of course. And the idea is that the further out you go in the perturbation expansion, then the more accurate it is. So that's that's the idea. And so what we're going to do in this class is we're not going to go any further than that for the eigenstate. But for the eigenenergy, it's common to go to second order. It's common to go out to second order in the eigenenergy. That's a common thing because it's not so hard. So let's do that. I've said this before, but I'll say it again. Like out in the real world, among theorists and people who are working on these problems in current day, people really do calculate the perturbation terms out further, like third order, fourth order, fifth order. They really do that. Some guy and more than one Nobel Prize has been obtained by going out to high order perturbation theory. Okay, so let's do the second order correction to the energy. So let's find the second order energy to the second order correction to the energy to the eigenenergy using perturbation theory. And so to do that, what we have to do is we have to go back to those equations that we derived, those perturbation expansion equations, and we got to use them. And so let's go back to the equation number 2, the second one. Remember how there was the zeroth order one, there was the zeroth order equation, the first order equation, and the second order equation. So let's use this one, the second order equation. And the second order equation, I'll rewrite it for you. We derived it, but this is what it is. It's this: H naught times the second order correction to the eigenstate plus H prime, the perturbation, times the first order correction.
So second order. Second order expansion of the Schrödinger equation is what? H naught psi n2 plus H prime psi n1 plus H. Is it just that? Yeah, because there's only one correction to the Hamiltonian. Is equal to E n naught psi n2 plus E n1 psi n1 plus En2 psi n naught.
To the eigenstate is equal to En naught, the unperturbed eigenstate, times the second order correction to the eigenstate plus the first order correction to the eigenenergy times the first order correction to the eigenstate plus the second order correction to the eigenenergy times the zeroth order eigenstate. That's it. And so it's not a very intuitive equation, but at least the superscripts all add up to 2. That's the only intuition that I can see here. So to solve this equation,
do the same trick.
we would use a trick that we've done before, and the trick that we would use
psi n The
can you guess
bra?
what the trick is that we're about to
Bra
do?
of cyan.
Same trick we used before to solve this equation. Can you
Not.
guess?
And a product with one of the unperturbed eigenstates.
Exactly. That's our favorite trick. We're gonna do it again. So what we'll do is we'll left multiply by using the bra, psi, and not. We'll take the nth unperturbed eigenstate and we'll left multiply it on both sides of the equation.
Yep.
Because if you do the same thing to both sides of an equation, it's still an equation. Still works. Okay, so let's do it. And so what we get then is this psi and not h naught psi n 2 plus psi n naught h prime psi n 1. So it's tedious, but it's simple. Just simple algebra. E and naught. You just kind of go through it, grind through it. Psi n naught psi n 2 plus e n 2 psi n naught psi n 1 plus e n 2 psi n naught times psi n naught. Okay, good. Now, one thing that we see right away is that here, this term here, this h naught, because it's a Hermitian operator, I can act to the left. And so when the h naught hits that guy on the left, what's it going to turn into?
E and not.
Someone tell me.
E and naught.
Exactly. So this term will be e n naught times psi n naught psi n2. Now, you might be thinking, oh my God, how do I know what psi n2 is? The second order correction of the wave function, which is an incredibly complicated formula. But we don't need to know it because you see that I have the same term on the right-hand side and I have the same term on the left-hand side. So what does that mean? Those terms do what?
Cancel.
They cancel. Yay. Yay. And then this one, of course, right here, what's this equal to? Someone tell me.
1.
Perfect. And so then, oh, and what's this equal to? What's that equal to? Yes, because remember, we're talking about that Hilbert space argument that psi n1 is perpendicular to psi n naught in Hilbert space. Remember that whole argument. So this thing is equal to 0. So I get to cancel them out. And so now we see that this thing becomes pretty simple. This big complicated formula turns into this. En2 is equal to psi n naught h prime psi n1. Okay, so that's as far as I can go. I cannot simplify further. And so there's nothing, I can't really simplify further. So what do I do now? Can you guess?
Plug in the result that we got for psi n1.
Exactly. That's exactly what we do. And where's that result? Oh yeah, here it is. Exactly. Exactly. That's exactly what we do. And where's that result? Oh yeah, here it is. Exactly. I got this formula. I will plug that formula in. That's exactly right. And so E n2 is equal to psi n naught h prime times that formula, and psi n1 is going to be the sum over all m except for m equals n, not that one. Psi m naught h prime psi n naught. The formulas are tedious, but easy. You just do it. Minus e m naught times psi m naught. Boom. That's it. That's right. And so now we see that this h prime is an operator. H prime is an operator. And so the thing to see is that this is just a number. It's just a number. So the operator doesn't operate on that. It's just a number. And so the operator sort of zooms all the way over here. It just slides right through until it hits that thing. So it just slides through until it gets stuck. It's like, can't go any further. It gets stuck. The operator gets stuck. You go over here. It's a number. It's just a number. So the operator doesn't operate on that. It's just a number.
That's a number because the expectation value is just an integral of a thing. Why is my webcam frozen? What the hell happened? What the hell? My normal webcam is fine. Another angle. Why is my Logitech webcam frozen? Let's unplug this. Will it break anything? I don't think so. Yeah. And we're back. Okay.
Number. And so the operator sort of zooms all the way over here. It just slides right through until it hits that thing. So it just slides through until it gets stuck. It's like, can't go any further. It gets stuck. The operator gets stuck. Because basically, in another way to think about it in terms of linear algebra, is that the operator is a matrix and this ket is a vector. And so a matrix hitting constants times a vector slides right through the constants until it hits the vector and then it gets stuck. So that's the way to think about it. At least that's how I think about it. And so let's move it all in there then. And so we see then that the second order correction is equal to the sum m not equal to n psi m naught h prime psi n naught times, you can put it on top, psi n naught h prime psi m naught divided by e n naught minus e m naught. Okay, you guys see that? All right, so that's what it is. Now there's something really cute. To notice, look at these two terms. What is the relationship between those two terms? Using your Brockett intuition from last semester, hopefully you guys.
One is a complex conjugate.
Yeah, exactly. Hopefully you guys sort of did some Brockett algebra last semester. Depends on who taught your course. Hopefully they did it, because Brockett algebra is very important to understand. That's right. These are complex conjugates of each other, and so that means that this thing then is equal to the sum over m not equal to n.
I ran out of tea. I kind of want to drink more tea, but I think we're at a time where it's normal water time. Normal water is boring though.
Psi m not a prime m not
Jesus.
absolute magnitude squared
Yeah, because these are real. I guess we assume they're real.
Times En naught minus En naught. And that is the answer. Put a little circle on it. So this is another very famous formula. And it gets 3 stars. It's a very important formula. People use it all the time. And so, okay, that's it. That's the second order correction. Now, the first time that you see this formula, it does not give you very much intuition the first time you see it. But it's actually a very important formula, and there is some important intuition that I want you to see. There's different ways of thinking about this formula. You know.
Look at this. This is the step that most professors would not take at this point. Of like, they would just show this and be like, okay, let's move on to the next thing. But it's so key to talk about the intuition, because nobody who's like a professor in this field or like actually does shit related to quantum mechanics, nobody when they think of it just thinks of the formula. Nobody is like, oh, the second order correction, that's easy. It's just, well, what's the formula? They think about like the idea behind it.
You know, people spend 100 years thinking about this formula. It's a really important.
If I tell you to memorize like apple, bat, monkey, banana, right? If I tell you to memorize that, you'll be like, I don't freaking know. Apple, bat, monkey, banana. Either you'll do some like musical like rhythm thing where you're like apple, bat, monkey, banana, or something like that. But the point of that is that you don't memorize like to memorize those things. You're not just like bringing it up out of a vacuum. You're associating something. You're associating this thing that you have to memorize with something that's more concrete. It's something that's like more intuitive, something that you don't really need to think about. So you're taking this thing that you need to memorize, and you're associating it with something else that it just comes very naturally to you. So something like rhythm, right? 1, 2, 3, 4. I don't have to think about being rhythmic. That's just something that's inherent to me, okay? Like that's just inherent to like pretty much all humans. All humans have a sense of like some sort of rhythm. So then like I can associate this weird apple, bat, monkey, banana thing with a rhythm, or I can just make up a story. So I can say an apple falls from a tree after a bat hits it, and the only one that sees it is a monkey across the street, and after looking at it, he takes a bite of his banana, right? You can come up with some story, so you're mapping these things that you have to memorize into something that's more key, which is like a story of like something falling from a tree, someone seeing it, and then someone eating something. Like that's basically the principle behind how do you teach something. I want someone to memorize something. Let me link it with something that comes more naturally to them. So in this case, quantum mechanics, I want someone to learn the second order, or I don't know the intuition behind that yet. So let's just think, I want someone to learn perturbation theory. How do I make them memorize that? Well, I have to link it to something that they already know. What's a picture that they already get? Well, from your last class, you would have gotten this picture of like Hamiltonians, right? So you know Hamiltonians, you know energy levels, you know that whole thing. So imagine perturbation theory is like taking that old picture, but then all you're doing is you're just tuning it by some amount to make it evolve into a new Hamiltonian. Like you gotta map these random things onto something that's concrete. That is how you teach, man. That is how you teach. And that is what so many people don't realize. How am I supposed to memorize the alphabet if you don't give me something that I can use to memorize it? How do you teach children? How do you teach children ABCs? You put it behind the song. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Because music is something that's very inherent to people at the most like fundamental level. Okay? So you don't have to think. You don't have to think of a melody. If I'm thinking of Sweet Child O' Mine, okay, I don't have to think of like what are the notes that he played in the melody. I just know it's like do 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 do. I know that. And then if you map the ABCs to it, it's like A B C D E F G H. Whatever, dude.
Whatever.
Whatever.
I'm not gonna go through all the different ways of thinking about it, but there's one way of thinking about that I personally have found very useful, and that's what I'll tell you. Here's the thing to notice. Like, how do I interpret this formula? Like, what's going on here? This is the way to think about it. I have all my unperturbed states, right, of H naught, and these are them. And so this is the one we're talking about, psi and not E n naught. But then there's the one above it, psi n plus 1 naught, E n plus 1 naught, psi n plus 2 naught, etc. E n plus 2 naught. And then this is psi n minus 1 naught, E n minus 1 naught, psi n minus 2 naught, E n minus 2 naught. Okay, so you have all these eigenstates. Now normally these eigenstates are all orthogonal to each other, and they're unperturbed Hamiltonian, and they don't mix. But now when I turn on when I go from H naught to H naught plus H prime, then the states mix. Remember, because psi, now all the states mix because psi n
naught is
is now equal to
superposition.
Psi n naught
Is that what you
plus
would
psi
say?
n1, which is this formula, not equal to n of H1 psi n naught E n minus m naught naught psi n naught. Okay, I got this formula. So this is the amount of mixing, and I talked about this formula last time and try to give you some intuition about that. So that's the mixing of all the states. But now let's look at this new result. And the point is that what's the way to think about it is that this En is a sum of this second order correction is a sum over all the unperturbed states. And so this is the thing inside of the sum is that the way to think about it is that each psi m naught contributes some energy to the state we're talking about. So the way is like each of the unperturbed states is giving a little bit of energy, is shifting, it's perturbing the energy of the state we're talking about. Every other state is mixing in with it and changing its energy. And so the question is, how much energy are all the other states contributing to the state we're talking about? And there's a simple way to think about it, because let's look at this formula. This formula is a sum. If I look at this formula, I have this.
Run that back, I'll sing something else.
This is the thing inside of the sum is that the way to think about it is that each psi m naught contributes some energy to the state we're talking about. So the way is like each of the unperturbed states is giving a little bit of energy, is shifting, it's perturbing the energy of the state we're talking about. Every other state is mixing in with it and changing its energy. And so the question is, how much energy are all the other states contributing to the state we're talking about? And there's a simple way to think about it, because let's look at this formula. This formula is a sum. If I look at this formula, I have the amount of energy that each state is contributing to the state we're talking about is this, squared over E n naught minus E m naught. That's the amount of energy. And so look at this formula and notice that if I'm talking about a state, so this is the state we're talking about, but if I look at the states above, then what can I say about this em naught relative to the en naught for the states above, the one I'm talking about? What can I say about that? I know I'm probably not making any sense, but I'm trying to make sense. So what is the relationship between the energy em naught of the states above, the one I'm talking about, and this is the one I'm talking about, gets a little star, and this is the energy of the state I'm talking about. What is the relationship between these two energies? Somebody tell me. That's a simple relationship. What is it? Yeah?
Em is bigger than En.
Yes, that's it. That's all there is. Exactly. For the states above, I know that em naught is bigger than En naught. Yes. And so what can I say about the denominator? Well, first, what can we say about the numerator? What is the sign of the numerator, the thing on top? What is it? The sign?
Positive.
Always positive. But what about the denominator? The denominator is not always positive. So if I'm looking at states above the state I'm talking about, what is the sign of the denominator?
Negative.
That's right. So En minus Em naught is less than 0 for the states above. So what does that mean? The states above, what is the sign? They're contributing energy to the state we're talking about via this second order perturbation theory. What is the sign of the energy that they're contributing to that state, the state we're talking about? What is the sign?
Negative.
That's right. Because I'll write like this. This thing is delta E. Actually, I don't want to write right there. I'm going to write right here. This thing is the delta E.
I don't get it. Why is Em not greater
between
than
these two energies? Somebody tell me. It's a simple relationship. What is it? Yeah?
Em is bigger than En.
Yes, that's it. That's all there is. Exactly. For the states above, I know that Em naught is bigger than En naught. Yes. And so what can I say about the denominator? Well, first, what can we say about the numerator? What is the sign of the numerator, the thing on top?
Oh. Em is any other state. And En is this ground energy. Oh, so of course that's going to be greater. So if Em is greater, then that's going to be negative. So it's going to be contributing negative energy.
What is Em naught is less than 0 for the states above. So what does that mean? The states above, what is the sign? They're contributing energy to the state we're talking about via this second order perturbation theory. What is the sign of the energy that they're contributing to that state?
Negative.
We're talking about? What is the sign?
Negative.
That's right. Because I'll write like this. This thing is delta E. Actually, I don't want to write right there. I'm going to write right here. This thing is the delta E M. That's the amount of energy given to the nth state by the nth state. That's right. And so the energy is negative. So all of the states above, are adding some energy to the nth state, and the amount of energy they're adding is negative. So the nth state moves in what direction energetically when it takes all that energy from the states above it? What direction does it move?
Down?
Down.
Yes, down. That's right. It's sucking all the energy, all the contributions of the energy from the states above is pushing down on it in energy. But now let's look somewhere else. Let's look at the states below. States below. And now, what is the relationship between En naught and Em naught? Somebody tell me.
EM is
Somebody
less than.
Now EM naught is smaller.
Now, which one is smaller?
EM. Naught.
Exactly. That's right. So En naught minus Em naught. What is the sign of that?
Positive.
Positive.
Yes, that's right. So all the guys below are adding some energy to En naught via the perturbation. So we're talking about it's the perturbation that's doing this. But the energy that all the states below are giving the nth state is now positive. So the states below are pushing it in what direction? Say it.
Up.
Up. That's right. Now this might just seem like just some weird thing, like wow, what a weird little thing to notice. But this is actually very profound and important, and this is an important part of your quantum mechanics intuition. Because what we've just shown is that I have a state. I'm talking about some particular state of some energy. If I have a state above it, then the perturbation is going to cause my state to move down in energy. But if my state is below it, the perturbation is going to cause my state to move up in energy. What does that mean intuitively? I will tell you. It means that the levels are repelling each other. They're repelling each other. It's like they're both negatively charged and they're repelling each other. You see what I'm saying? If a state is above, then by the second order perturbation theory, it pushes my state down. If the state is below, then by second order perturbation theory, it pushes my state up. So levels are repelling each other. And I'll just say that it has a name. It's called level repulsion. Now, the reason I'm making a big deal about this and spending a bunch of time on this is because this is an important part of your quantum mechanics intuition. People always are talking about level repulsion, and it's very common that when you have levels close to each other, they repel each other. You turn on a perturbation and the levels repel, and it's just a common thing. Everybody just knows it, but many people don't remember where it even comes from. And so this is where it comes from. Okay, second order perturbation shows that levels repel. So this is a new piece of quantum mechanics intuition that you now get from perturbation theory, and it's not obvious at all. I mean, if someone said to you, "Hey, levels repel each other," you'd be like, "What the heck are you talking about?" I mean, it makes no sense, and yet it's true. It's a real thing. The perturbation causes the levels to repel, and that's also quite interesting because now, if I look at this, now let's look at the ground state. And if I'm looking at the ground state, then notice that I have all these eigenstates of the unperturbed Hamiltonian, but only one of them is the ground state. I'll call it psi ground state, 0, okay? And then the ground state means that all the other states are above it. The ground state is the lowest energy by definition. And so let's ask ourselves, so let me ask you a question. What is the sign? I mean, all these states above the ground state, by second order perturbation theory, what direction are they pushing the ground state? Are they pushing the ground state up in energy or down in energy? Somebody tell me.
Down?
Down.
That's right. All of them by level repulsion are pushing the ground state down. There are none below it, so there's nothing counteracting that. There's nothing pushing the ground state back up. And so what that tells us is that the second order correction to the energy for the ground state, the second order correction to the ground state energy via perturbation theory always has what sign? Positive or negative?
Negative?
Negative.
So this is pushing it down?
It's always negative. That means by second order perturbation theory, we always lower the energy of the ground state. And that's sort of, it's like an obvious thing to notice just by this kind of simple mathematical reasoning. But it's a profound thing because it means that whenever you have a ground state, if you calculate the second order perturbation theory, that will always lower the energy of the ground state. And so people often use this. They're always like saying, "Oh, what's the preferred ground state?" Well, you can use second order perturbation theory to help you see what is the preferred state. The second order correction to the energy always lowers the ground state energy. So it's a good way to get more insight into what the ground state is doing. And so people use it all the time. It's a very important trick in quantum mechanics. So it lowers the ground state energy. Okay. So that's kind of all that I want to say about that. I think I beat that into the ground. And so now I'm not going to give an example of that. I think you might have some examples in your homework. I'm not just going to grind through some formulas. I think that's all I want to say about second order perturbation theory at this point. Yeah, Varun.
Yeah, so I was wondering, does that always mean that the ground state energy is lower, or could we have, let's say, a larger positive first order correction? I mean, can we always tell the sign of the final ground state energy just from the second order term?
The sign of the ground state energy from the second order term?
Sorry, not the sign, but the sign of the direction it changes in. Because what if you have a larger but positive first order correction?
And so you're asking me what? Yeah, I mean, I guess I'm not exactly sure how to answer your question. I mean, the second order correction always lowers the energy. I mean, by this little formula we just derived. I guess I don't quite understand your question. I'm sorry.
Okay, so let me try again then. So let's say we have a large but positive first order correction.
Okay, you're saying the perturbation is positive.
Yeah, and then the second order perturbation is negative, but that could still result in like a net positive change to the ground state energy, right?
No, it cannot. I mean, we just derived a formula. The formula is unambiguous. I mean, we're just looking at it. I mean, the formula is always negative. So I guess the funny thing that is weird to you is that this positive perturbation can lower the energy. I think that's what's freaky to you.
Not exactly. I mean, if we include the first order term as well, I mean, are we including that?
Oh,
or are we just looking at the second order term?
I'm just talking about the second order term.
Oh, okay.
I'm just talking about the second order term. Okay, I'm not saying relative. No, the first order term. You're right. The first order term could be very positive. Yeah, you're right. So the total perturbation could raise the energy, but I'm just talking about the second order term. Okay, is that clarify?
Yeah. Thank you.
Okay. And also I will say, you don't have you can just shout out. You don't have to like hit the raise hand button, because I might not notice it if you hit that button because I might not be looking at the screen. So just shout out if you have a question. It's okay to interrupt me. Even though I get on a roll, but it's okay to interrupt my roll. Okay. Now let's talk about time to talk about degenerate perturbation theory. Yay, degenerate perturbation theory. So this is a really cool topic, actually. I've grown to love degenerate perturbation theory. I remember as an undergraduate, I really hated it because it was so confusing. I remember, I had terrible quantum mechanics teachers when I was an undergraduate. And it was all just a big confusing mess and I didn't understand anything, even though I was very good at the formulas and I could do all the formulas very carefully. And I was so proud of myself.
He's speaking to me.
I remember as an undergraduate, I really hated it because it was so confusing. I remember, I had terrible quantum mechanics teachers when I was an undergraduate. It was all just a big confusing mess, and I didn't understand anything, even though I was very good at the formulas and I could do all the formulas very carefully. And I was so proud of myself. I could write them all down and derive them all. But I actually had no clue what any of it meant. It wasn't until graduate school that I started figuring out quantum mechanics. And degenerate perturbation theory was just like a confusing mess to me, and it just frightened me, and I hated it. But now
He's speaking to me, but I'm not saying that my professors are terrible. They're just terrible at teaching quantum mechanics in a way that I understand it. I'm gonna get another printer paper. Running out of printer paper, running out of printer paper. My back. Oh, my back. My aching back. More printer paper. We got some more printer paper. Imagine if you could do this with lectures like that were like happening in the real world. You can just pause it and be like, "Hold on! Wait, professor! Let me get some McDonald's," or something like that, you know? I'm just looking outside and I'm like, fuck. If only I was outside, man. Outside fucking sucks around here, though. It's just a city of, like, shitty trash, man. This place sucks. Outside is shitty, inside is shitty. What the fuck is there redeeming about this place, dude? Oh, let me go outside to explore shitty sidewalks and let me get a bite to eat. That'll just be $20 per person. Wait, let me get some groceries. That'll just be $40 for 3 things. Dude, fuck. Oh my god, I'm losing my mind. It's not funny, it's just so fucked up that you just gotta, you can't help but laugh, you know? Oh my god, oh my god, oh my god. Oh my skibbity Ohio 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 god. Whoa, oh, oh, oh. Yeah, I'm just catching up with messages. You know, I'm a pretty popular guy. Just catching up with some messages. Okay. Degenerate perturbation theory.
No, I really love it because it's so simple and beautiful. And so I will try to give you some sense of the simplicity and beauty of degenerate
Gotta turn up the brightness on my monitor.
perturbation theory, although it might not be totally obvious to you that in the first minute. But think about it, and eventually, hopefully, you will see that it's a very simple, beautiful thing. But it's just can be taught really horribly by some people. Okay, so let's see. Let's try to do it. So, okay, here's the deal. So
Also, that's those are some like strong words to put out before you teach something. To say like, man, my quantum mechanics professor sucked when they were teaching us. Now I'm gonna teach it. That's kind of like you got to put a lot of faith in yourself to be like, I have a good ass explanation.
let's write it down. I have this. I have from perturbation theory. We have the perturbation expansion. For h equals h naught plus h prime. We have our eigenstate is equal to psi n naught plus this term m not equal to n of psi m naught h prime psi n naught e n naught minus e m naught psi m naught. And I have my energies. Actually, I'm gonna do this. Maybe I'll always do this, the wiggly sign, to show that it's an approximation. E n naught plus psi first order correction plus the second order correction. M naught h prime, the one that we just derived. Okay, all right, that's what we've done so far. I just wrote it all out, okay? That's everything that we've derived so far. Now, I just want to say that we love this. We love the perturbation expansion because it's so simple. Because it just tells us, if someone gives you some weird Hamiltonian h prime, you just plug it into these stupid formulas, which are actually fairly straightforward to calculate, and you from the unperturbed states, you just get the answer. So physicists love these formulas. We just love them, and we want to use them whenever we can, and they give us lots of intuition. I've told you some of the intuition already, and so we just really like these formulas a whole heck of a lot. But there's a problem. There's a fly in the ointment. A big cockroach floating in the cereal. Have you ever had that? Found a cockroach floating in your cereal? I have. I'm telling you, it's not a pretty thing. Okay, so we got this problem. What is the problem, folks? What is the fly in the ointment? What is the cockroach floating in your cereal? Somebody tell me.
If En equals Em, then it blows up.
Exactly. Then blows up. That's exactly right. It blows up. That's right. It diverges. There's a singularity. It's singular. That's right. And you can just see that because in the denominators, right? There it is. Boom. So the denominator, if denominator goes to 0, then that's a big problem. And of course, what that means then, and what does it mean for En to equal Em? That means that the states are degenerate. That's the definition of degenerate states. So if there are degenerate states, then that's a problem. If you have degenerate states, it destroys our beautiful formula that we love so much. It wrecks it. So degenerate states wreck the formula. Wreck the formula. But we love the formula. How can we save the formula? Must save the formula because we love it so much. Or formulas must save the formulas because we love them. And you always want to save the one you love, right? We all know that. Okay, so how do we save this formula? Okay, well, can someone tell me one way that the formula might be saved? Like, what will save the formula from diverging? Can somebody tell me? How can we save the formula?
If the numerator goes to 0, then the denominator doesn't matter at all.
I mean, can we just discard terms that have equal energies in the denominator?
No, because they're infinite. They're part of the formula. They're in there, and they diverge. You can't just ignore it. But under what conditions might the formula be saved? Look at the formula, and suppose I do have degenerate states, but there is a special condition. I might have degenerate states, but under a very special condition, the formula is saved. What is that condition? And you can see it by just looking at the formula. And it's not like a super subtle thing, because look, the denominator is going to 0. That's killing us. What would save us?
Having the like the numerator be 0.
Yes, that's it. So simple. Exactly. If the numerator was 0 and the denominator goes to 0, then assuming the right conditions, then the thing is not singular. It could actually limit right to a nice number. You guys all know that. Like, let's look at an example. What's our favorite example of that? I think everybody's favorite example of that is the limit of x goes to 0 of sine x over x, right? That equals 1. If I remember correctly. Is that right? Yeah. Limit of sine x over x is 1, right?
Yeah.
Okay. Yeah. Okay. So that's our favorite example of that kind of thing. Okay. So I'm not going to get into all the mathematical nuances of which one's going to 0 faster. I mean, those are subtle mathematical subtleties I don't want to get into. But the bottom line is, we can save the formulas. The formulas are saved. Formulas are saved if the numerator equals 0. In other words, and so now I'm going to lose those formulas. Oh, there they go. The formulas are saved. We are saved if basically psi m naught h prime psi n naught equals 0. So the thing that hurts us, the hurtful thing is if E m naught equals E n naught. That's what hurts us. because then the denominator goes to 0. But we are saved if the numerator also goes to 0, okay? So one thing hurts us, the other thing saves us. So so the point is, okay, so the point is that if our degenerate states, so here's the thing. Basically, so the whole point of degenerate perturbation theory is to find, okay, so this is the whole point of degenerate perturbation theory. Degenerate perturbation theory, the whole point is to find a new basis such that psi m naught h prime psi n naught equals 0. That's the whole point. That's the whole point of degenerate perturbation theory. Because, I mean, here, check it out. Like this is, let me try to draw it graphically, but that is the whole point. That's it. So here's the way to think about it. I have my Hamiltonian h naught, and I have my states, okay, my ladder of states. And these states are not degenerate, the ones I've just drawn. Not degenerate. But then suddenly I have some degenerate ones. 1, 2, 3, 4. And then I have a bunch of non-degenerate ones, let's say. So then what I do, so that's my situation, okay? But now what I do is now I turn on perturbation, and everything's fine. This is my unperturbed, those are my unperturbed states, and these are, you know, all the energies. That's the ground state energy. This is E1 naught, E2 naught, E3 naught. You know, I know all those energies. E4 naught. But now here at E5 naught, I have 4 degenerate states, and this is E6 naught, you know, E7 naught. Okay, so I have all that, but I have some degenerate states. So now what I do is I turn on my perturbation. H goes to H naught plus H prime. I turn on my perturbation. And then I ask you, I say to you, what happens to all of these states? How do their energies change? How do the wave functions change? What do they do? And what you say to me is you say, well, you know, then I get you know, suppose I give you some really hard H prime that you don't know what to do with. So the only trick that you can do, the only thing you know how to do is use perturbation theory to figure out how the eigenenergies change in the presence of this perturbation. You have to use perturbation theory. And so you start using perturbation theory. And what you say to me is you say, well, you know, then I get you know, suppose I give you some really hard H prime that you don't know what to do with. So the only trick that you can do, the only thing you know how to do is use perturbation theory to figure out how the eigenenergies change in the presence of this perturbation. You have to use perturbation theory. And so you start using perturbation theory. And you use perturbation theory on all these non-degenerate ones. And it's really simple. It works, right? You just plug into the formulas. So for the non-degenerate states, you plug into the formulas that we love. But then you get into the degenerate states. And now, you go to this degenerate states. And by the way, I'll call that a degenerate manifold. What is the dimensionality of the degenerate manifold that I have shown in this little picture I just drew? Somebody tell me.
4.
That's right. So this is a little 4-dimensional mini Hilbert space, right? Hilbert space. As a 4-dimensional mini Hilbert space. Now nobody wants to say 4-dimensional mini Hilbert space, so instead I'll just call it the degenerate manifold. But when I say the word degenerate manifold, what you should think of is like it's a little mini Hilbert space. With the dimensionality of that space is simply the number of degenerate states. Okay, so now you get to this degenerate manifold, and I'm saying to you, okay, what does the perturbation do to this degenerate manifold? And so what you want to do very quite naturally is you want to plug into your little formula. You want to plug into those formulas that we have, because that's all you know. Use those formulas, and you love them. We all love them. So you plug into the formulas. Now, what is the nicest thing that could happen to you if you plug into those formulas? What would be the nicest thing that happens to you? If I'm asking you, I'm saying, how do those states, you know, what does the perturbation do to those states? So you plug into those formulas, and what's the nicest thing that could happen? Somebody tell me. These are the formulas, by the way. I'm showing them to you right now. We're trying to figure out what these degenerate states do in the presence of some perturbation. And so you plug into the formulas, and I'm asking you, what's the nicest thing that could happen to you?
Like the equations we already have for them end up, when you do the psi m0, h prime psi n0 end up being 0.
Yes, exactly. The nicest thing that could happen to you is if the numerator is 0. Nice if equals 0. That's right. If the numerator in the formula equals 0, then in the degenerate manifold, your perturbation expansion won't blow up. And so the point is that you plug in, and then if the numerator equals 0, in other words, if psi m naught h prime psi n naught equals 0 for the degenerate states, where these are degenerate states, then the perturbation expansion is good. Oh my God, the formulas work. Yay. And you're happy because life is sweet, life is simple. You don't have to do nothing more. You just plug into the formula and it works. In which case you can see then that you can just see that psi n naught, then you just plug into your formulas and they work. Psi n is approximately equal to psi n naught plus psi n1, and en naught, en is approximately equal to en naught plus en1. Let's just go to first order. All right? And so you're good. You plug in and everything's good, and you don't have to worry about these infinities. There are no infinities. Okay? Because look, you can't just ignore infinities. You know, if your perturbation expansion has some infinity, you cannot just ignore them. You know, unless you're Richard Feynman, but let's not worry about that. And for us, in undergraduate quantum mechanics, if our perturbation expansion has some infinity, we cannot just ignore it. It screws everything up. Okay, but if the numerator goes to 0, then there are no infinities. The formulas work because there is no infinity. And then you just plug into your formulas and everything's sweet and good. Okay, but what if? So first I should say that when you're doing a physics problem and you're using perturbation theory and you have a degeneracy and you want to use your perturbation theory, what is the first thing that you should check? Well, I guess it's kind of a trick question. What I want you to say is the first thing you check is to see if these numerators equal 0 or not. That's the first thing to check. And let's use a name. Let's use a word, because remember, you know, H prime is an operator, right? But that means that the perturbation is an operator, is a matrix. And that means then that if I show you this thing, psi m naught h prime psi n naught, what is that thing? If the operator is a matrix, then what is this thing? What do we call this thing? I've been calling it the numerator, but what should I call it instead?
Matrix element
Of what?
of the operator.
Exactly. It's the matrix element of h prime. So this is the matrix element of h prime. That's right. Now, if m does not equal to n, then what can I say about this matrix element? I know that h prime is some matrix. It's some matrix. But if m does not equal n, then this matrix element is what? What can I say about that matrix element?
It's
Where
off
does it-
diagonal.
Yes. It's the off-diagonal matrix element. Now, this is just language. Because, we derive this formula, this perturbation expansion formula. And so a really cute, funny thing that we're now noticing is that in these formulas, what we're summing over in these formulas are the off-diagonal matrix elements of the perturbation. What a funny thing to notice. All right, I'm just telling you, there it is. These sums, we're summing over the off-diagonal matrix elements. So we're doing sort of like this weird sum over off-diagonal matrix elements of the perturbation. And so the point I want to make is that what we have is if we have a degenerate subspace, then the whole point is to see in this little degenerate subspace, what is the value of these off-diagonal matrix elements? So let's restrict ourselves to the degenerate subspace, because the degenerate subspace is the only place where we're going to get these singularities, these infinities. And so we got to fix it. The problem is lying in the degenerate subspace. And so the problem lies there. It's in the degenerate subspace. That's where the problem lies. And so basically, if the off-diagonal matrix elements in the degenerate subspace are 0, then there's no problem. The formulas work. But now let's go to the horrible case. But on the other hand, if psi m naught h prime psi n naught does not equal 0, then what? Now I have this horrible problem that I have these formulas which have this term in them. H prime psi n naught over em naught minus, I'm sorry, that's en naught minus em naught. I have these terms in my perturbation expansion, and if this is true and em naught equals en naught, if both of these things are true at the same time, then you are screwed. Because now I'm telling you, I'm saying, for this problem, I want to know what does the perturbation do to these degenerate states? And if both of these things are true, then you are screwed. You are screwed. Because the formula diverges. And all that you know is those formulas, all right? That's all that we know is the perturbation expansion formulas. You are screwed. Your formulas diverge. Okay, but it turns out that we can fix things. We can fix things. And the fixing is called degenerate perturbation.
So this H prime is off diagonal matrix elements? How can I understand that better?
Formulas which have this term in them. If we have a degenerate subspace, then the whole
H prime is an operator, which means it can be expressed as a matrix. So this is a matrix element? What is a matrix element? Oh my god. See, like, bro, Google is just fucked, man. You just saw a pure example of Google just feeling like horrible. A matrix element refers to an individual value or entry in a matrix, which is a rectangular array of numbers, symbols, blah, blah. Okay, yeah. So this is a matrix element of H prime. Why is that a matrix element of H prime? If m does not equal n, H prime is some matrix.
whole point is the matrix element in these formulas. It's the off-diagonal matrix element. It's some matrix. But if m does not equal n, then this matrix element is what? What can I say about that matrix element?
It's off diagonal.
Yes. It's the
Oh, because m does not equal n, so this is like mn. So m, if m equals n, then that's the diagonals. But if m does not equal n, then that's the off-diagonal parts. Okay, that makes sense.
off-diagonal matrix
So
element.
you're taking a sum of these matrix elements, but m does not equal... shut the frick up, Siri. So you're taking a sum of these matrix elements, but you don't let m equal to n. So these matrix elements are all of the off-diagonal parts.
Matrix elements. So let's restrict ourselves to the degenerate subspace, because the degenerate subspace is the only place where we're going to get these singularities, these infinities. And so we got to fix it. The problem is lying in the degenerate subspace. And so the problem lies there. It's in the degenerate subspace. That's where the problem lies. And so basically, if the off-diagonal matrix elements in the degenerate subspace are 0, then there's no problem. The formulas work. But now let's go to the horrible case. But on the other hand, if psi m naught h prime psi n naught does not equal 0, then what? Now I have this horrible problem that I have these formulas which have this term in them. H prime psi n naught over em naught minus formulas, all right? That's all that we know is the perturbation expansion formulas. You are screwed. Your formulas diverge. Okay, but it turns out that we can fix things.
I'll write this down. So H prime is a matrix, since H prime is an operator, therefore psi m naught of H prime psi n naught is a matrix element of H prime. And since n is not equal to m,
we can't fix things. And fixing is called degenerate perturbation theory. How can we fix it? How can we fix it? Before I say the answer, let's look back at the problem. Because I want you to sort of see the key to degenerate perturbation theory. There's something really simple here. Maybe I'm using a lot of new words, it's very complicated, but there's something really simple at the heart of it. I want you to look at this example that I gave you. How many degenerate states did I give you in this example? How many?
4.
That's right, 4 degenerate states. Now I said that these are the degenerate states, and let's just call them, I'll just call them psi A, psi B, psi C, and psi D. There's 4 of them. And they are eigenstates, because if I hit the Hamiltonian H naught up against psi A, then that equals E5 naught psi A, right? And if I hit H naught up against psi B, then that equals E5 naught psi B. They are degenerate eigenstates. They have the same energy when I hit them with a non-perturbed Hamiltonian. But now let me ask you a question. What happens if I hit the sum of 2 of them, psi A plus psi B, with the Hamiltonian? Then that equals something times psi A plus psi B. What is the energy? What is the eigenenergy? If I take 2 degenerate states and add them together and create a new state, let's assume it's properly normalized to some multiplicative factor that I'm ignoring. What is the eigenstate of this superposition, this arbitrary superposition of 2 degenerate eigenstates? What if I hit H naught up against that? What is in front? Somebody
E5.
The same energy, E5.
That is right. That's the beautiful thing. The whole point is that if I have a degenerate manifold, then my eigenstates are somewhat arbitrary, because any linear superposition of eigenstates remains an eigenstate. What that means is that there's just many different possible bases within that degenerate subspace. I could do psi A, psi B, psi D, or I could do psi A plus psi B, psi A minus psi. I could come up with arbitrary linear superpositions. The point is that there are many arbitrary superpositions of degenerate eigenstates. The point is that you have there are many possibilities that the degenerate eigenstates are sort of not, they're sort of ill-defined in a way. Like you can calculate them, but then you could create arbitrary superpositions, and those superpositions would also be degenerate eigenstates. And that's kind of an obvious thing from linear algebra. Okay, so the point is that the point I'm trying to make is that in the degenerate subspace, we have many choices of how we choose our eigenstates. Many choices of the eigenstates. So here's the question. Which choice is the right one? Which choice does nature choose? Okay.
What did he just say?
And that's kind of an obvious possibilities that the degenerate eigenstates are sort of not, they're sort of ill-defined in a way. Like you can calculate them, but then you could create arbitrary superpositions, and those superpositions would also be degenerate eigenstates. And that's kind of an obvious thing from linear algebra. Okay, so the point is that so the point I'm trying to make is that in the degenerate subspace, we have many choices of how we choose our eigenstates. Many choices of the eigenstates. So here's the question. Which choice is the right one? Which choice does nature choose? Okay, which choice does nature choose? Well, let's ask ourselves that question. So let's consider the energy of our state. The energy of one of those degenerate states, let's say En, is equal to En naught plus psi n naught H prime psi n naught plus M not equal to N psi M naught H prime psi n naught over E n naught minus M naught squared. So this is the formula for the energy of one of the, so in the degenerate manifold, this is the formula for the energy of the n state in the degenerate manifold. But we have many choices for the eigenstates in the degenerate manifold. So which eigenstate should I plug into this formula? I don't know which one, because I have many choices. Did you see that? I have many choices. Because I could create different linear superpositions within the degenerate manifold. So which is the choice that nature chooses? Well, let's consider for a second. If I make a choice such that this numerator does not equal 0, then my energy goes to what? Somebody tell me.
Infinity.
Yes. So on the other hand, if I make a choice for degenerate eigenstate such that this equals 0, then my energy is finite, right? So which choice does nature choose? I have choice 1 or I have choice 2. Which
Choose
choice do you think
2.
nature
We'll
chooses?
try
1 or 2?
to keep the energy finite.
Does
2.
nature, what?
2.
Yes, because nature hates it for energy to go to infinity. Nature hates that. It's terrible because it costs a lot of energy. Yeah, and nature obviously hates that. Nature doesn't like energy to diverge. So nature chooses this one. Yes. So of all the many superpositions of the degenerate eigenstates, nature chooses the superposition that causes the energy to not diverge. It's kind of obvious. Like, of course it would do that. I mean, if I had many choices, of course, nature's going to choose the one that makes the energy not go to infinity. I think that's kind of obvious. Okay, which choice is that? Which of all the different superpositions of the degenerate eigenstates, what is that magical superposition that causes this off-diagonal matrix element to go to 0? Because for my energy to be finite and for my perturbation theory to work, then I need these off-diagonal matrix elements of H prime to go to 0. So nature is saying in the degenerate subspace, nature wants the off-diagonal matrix elements to go to 0. What does it mean if your off-diagonal matrix elements are all 0?
You've written H prime and its eigenbasis.
Yes, yes. Because if your off-diagonal matrix elements are 0, that means that your matrix is diagonal. It's diagonal. If the off-diagonal matrix elements of H prime go to 0, that means that H prime is diagonal. But if H prime is diagonal, that means that the states you have chosen are the special states. What states are they? Say it again.
The eigenstates.
Yes, yes.
Wait, are they eigenstates though?
You've written H prime and its eigenbasis.
Yes, yes. Because if your off-diagonal matrix elements are 0, that means that your matrix is diagonal. It's diagonal. If the off-diagonal matrix elements of H prime go to 0, that means that H prime is diagonal. But if H prime is diagonal, that means that the states you have chosen are the special states. What states are they? Say it again. Again?
The eigenstates.
Yes, yes.
Wait, are they eigenstates though? Right? I mean, don't we still have mixing from the...
Diagonal. But if H prime is diagonal, that means that the states you have chosen are the special states. What states are they? Say it again.
The eigenstates.
Yes, yes.
Wait, are they eigenstates though? Right? I mean, don't we still have mixing from the states, like
Let me
other
just say
states?
they're eigenstates in the degenerate
In the
subspace.
manifold.
That
Yeah.
fixes the problem. Because that's the whole point. H prime is diagonal in the degenerate subspace. So the whole point is that this is the whole point. To make the perturbation expansion work, I want the formulas to work, damn it. To make the perturbation expansion formulas work, then we need H prime to be diagonalized in the degenerate subspace. And that's it. That is degenerate perturbation theory. It's just so simple. It's like sort of simple and obvious. You know, it's like there's no real trick to it. We're just trying to make the stupid formulas work. And the only way we can make the stupid formulas work is to diagonalize H prime in the degenerate subspace. If we diagonalize H prime in the degenerate subspace, the formulas work. If we don't, they don't work. That's it. That's degenerate perturbation theory. I just want you to see there's something really simple there. I mean, it might seem confusing to you if you're not familiar with all this linear algebra lingo. You know, like if your linear algebra if you're really weak, if your linear algebra is weak, then this might seem really complicated to you. If that's the case, then sort of try to remind yourself of all that linear algebra stuff. But from a linear algebra perspective, it's really quite simple. The whole point is that we have this degenerate subspace. I'll go back to it. Here it is. There's my degenerate subspace. And the whole point is that we got to find the superpositions of these degenerate states, and we got to formulate a new basis. So the whole point is that we must find a new basis, a new degenerate basis, and I'll call it this, psi m, the set of states psi m naught bar. That's my new degenerate basis, such that the off-diagonal matrix elements in the degenerate subspace equal 0. That means then that this state psi m naught bar are the eigenstates of H prime in the degenerate subspace. Okay, and so we just have to find that. And once we find those states, then everything is sweet, because now psi in the degenerate subspace, then what happens is psi n is equal to this new basis, psi n naught, and en is equal to en naught plus psi n naught H prime psi n naught. where this is the new basis. So where these are now the eigenstates of H prime. Okay, so that is degenerate perturbation theory. That's it. We just did it. We just did the whole thing. The whole point is that I diagonalize H prime in the degenerate subspace, and then my wave function, my eigenstates are these new eigenstates of H prime. And my energy, my new perturbed energy is like now I can use the perturbation expansion. Now it works, and I only go to the first order. And so, but the point is I have to use my new eigenstates, and I just use the first order result of the perturbation expansion, and it's okay because the other terms are not infinity, and that's it. And that's degenerate perturbation theory. Okay, so I hope that makes some sense or wasn't too crazy. But now let's do some examples. Let's do an example. And so my favorite example of degenerate perturbation, we're gonna do many examples. We're gonna do the fine structure of hydrogen. But first, my favorite example of degenerate perturbation theory, my personal favorite, is covalent bonding. Because you can think of covalent bonding between atoms as an example of degenerate perturbation theory. It's a result from degenerate perturbation theory. Covalent bonding is what holds together atoms in the molecule. So it's sort of the most fundamental, depends on your point of view, but it's what holds us together. It holds us together. So it's a pretty important thing. It's the thing that holds us together. And so it's pretty fundamental. It is literally the thing that holds atoms together. Okay, so it's like really, really fundamental. It is the basis of all chemistry. Basis of all chemistry. And so let's try to understand covalent bonding as a simple example of degenerate perturbation theory. So let's do it. Maybe what I'm going to do is I'll just sort of set it up. I don't think I have enough time to go through the whole thing, but let's consider it. Let's take two atoms. And here are the atoms. I have a Coulomb potential, and let's just say this is meant to be V and R, and then so here's my wave function. So I have some eigenstate. I'll call it phi naught. Just use the same notation that I use. I'll call it phi 1 of R. Okay, I have some orbital of an atom. So this could be like the ground state of a hydrogen atom. And so I'll call that atom 1. So that's atom 1. And there's a nucleus here, right? That's attracting the electron. So that's the electronic eigenstate. Now let's take another atom, atom 2. And it also has the ground state. I'll call that E naught. And it also has a ground state E naught. And I'll call that phi 1, phi 2 of R. So this is, I have two atoms, atom 1 and atom 2. Now, if the atoms are far apart, then we see that everything is the same. I have the energy is E naught. And so what I do is, here's the way to think about it. Let's take the two nuclei, and this I'll call nuclei number 1 and nuclei number 2, and let's take an electron, and let's throw it in. Now, if I throw it, because we're just talking about one electron at a time, just one electron. We're only talking about one electron. In perturbation theory, we're only talking about one electron. So I can throw my electron, so I can throw my electron either into this nuclei atom 1 or into this nuclei atom 2. And if I throw it into atom 1, then it's going to sit in this state, phi 1. But if I throw it into atom 2, it'll sit into this state, phi 2. And so those two states are the same. The energies are the same. So phi 1 and phi 2 are degenerate. But now let's do something. So those are two degenerate states. Because if I throw it into this atom, if they're far, then they don't feel each other. Don't feel each other. But what if they get near? What if they get near to each other? If they get near to each other, then they feel each other. For example, now I have atom 1 here and I have atom 2 here. But now near means that these wave functions are starting to mix. If the wave functions start to mix, they feel each other. And what that means is that if I have an electron going into this atom, it feels, what does it mean to feel each other? What that means is that the electron in one atom feels the tug of the other nucleus. Electron feels the tug of the other nucleus. What should we call that tug? So I throw an electron into atom number 1. So electron in atom number 1 feels the tug of nucleus number 2. What is the effect of that tug? The question is, what does that tug do? The answer is that tug causes chemical bonding to occur. It causes chemical bonding. That is the origin of chemical bonding. How can we see that from a degenerate perturbation theory perspective? What we do is we take the tug of the other nucleus, and we give it a name. What do we call it? We call it H prime.
Yeah.
Perturbation. The tug of the other nucleus is perturbing the state. So as the two atoms come together, the electron in this atom feels the tug of that nucleus, and vice versa. So the electron here, the electron starts feeling the tug. This electron feels the tug of this nucleus, and this electron feels the tug of that nucleus. So this is the tugs I'm talking about. The tug. That's the tug I'm talking about. And that tug is the perturbation H prime. And so then what happens? So how does the presence of that tug change the states? Okay, so basically what you would do is you would say, well, that's simple. I'll just do perturbation theory. But and what is the dimensionality of so I only have two states. There are only two states that I'm talking about, phi 1 and phi 2 for these two atoms. Phi 1, phi 2. I got these two states. But then if I want to use perturbation theory, then we ask ourselves, they are degenerate because E naught 1 is equal to E naught 2. They are degenerate. And so then if I turn on my perturbation, then I have to ask myself, if I have state 1, and if I have my perturbation, will this off-diagonal matrix element, is it equal to 0? Yes or no? So that's the question you have to ask yourself for degenerate perturbation. Does this off-diagonal matrix element equal 0 or not? And so the point is that an electron, the point is that it does not equal 0. Phi 1 H prime does not equal 0 because the tug of the electron, the tug of the nucleus on an electron far away, there's no symmetry. There's no reason why that matrix element would equal 0. You know, if you try to calculate it, you'll find that it's some god-awful horrific formula, but it does not equal 0. And so the point is that you cannot solve this problem easily. And so basically what you have to do, and we don't really have time to do it all, but what we must do is construct the matrix of H prime in the degenerate subspace and diagonalize it. Because that's what degenerate perturbation tells us to do. So we have to then construct. So
that problem's going to be really hard. God damn it.
And so that means then that our perturbation is living in a two-dimensional subspace. So that means that the matrix is a 2x2 matrix. So we have H prime 1 1, H prime 1 2, H prime 2.
Oh, this is a homework problem though, right?
Where H prime 1 1.
Yeah, this was a homework problem.
H prime phi 1, H prime 2 2. You can just write down all of these matrix elements.
Yeah.
H prime 1 2 is phi 1, H prime phi 2, and H prime 2 1 is phi 2, H prime 1. And by symmetry, we expect these guys to be the same. These two should be the same, and these two should be the same. So without even knowing what they are, we can solve the problem because we have H prime is equal to alpha, beta, beta, alpha, and then to find, then we need to find the eigenstates. We must diagonalize it. Diagonalize it. And so when you diagonalize this matrix, and sort of we kind of have run out of time, but I just wanted to just give you a sense of if you diagonalize it, then you can find the eigenenergies. And I'm not going to diagonalize it because it's a 2x2 matrix. You've done that before. But if you find the eigenenergies, I'll just write the answer. The eigenenergies are lambda equals alpha plus beta and alpha minus beta. And the eigenstates are, I'll call this, and the eigenstates are going to be, this one will be phi 1 plus phi 2, and this one, the eigenstate will be phi 1 minus phi 2. These are the eigenstates after you diagonalize it. And so I guess we didn't have enough time to do it.
Okay. Makes sense. X. So now... Wait, I didn't want to close that, actually. Recently closed. Open this up. Add it to that. Oh my god, my computer's on 20% now. Okay, so I can live stream for like what? I feel like I took out my battery like pretty close, but computer's on 19% now, so we'll plug it back in. Boom, you've just been plugged back in. You got juice. You're juiced up now. So yeah, so now what? Now we go through homeworks, right? And we try to understand what's going on here. So let me put that back. Let me pull this one out. I'll pull out all of the solutions. Solution for homework 3 should have been posted by now. Let me download that. Yes. It was posted this morning, actually. Jesus. Okay. So now we got the solutions and we got the problems on either side. Let's make the problems a little bit smaller, solutions a little bit bigger. And now what we have to do is we just have to grind out these. That's all we have to do now. Let me put the solutions on the left. Which one's better for the stream? I can't believe I'm thinking about that. Yeah, put the solutions on the left, problems on the right. Because the problems are cut off a little bit, then who cares? But okay. We're going to ignore... Actually... So, one thing that he did mention... And I think this could be on it. think this could be on the exam. So, properties. For conservation laws, we'll have another. Does that show up normally? Okay, yeah, it just shows up like that. So, changing basis. Because I'm pretty sure he mentioned that. He mentioned like something where he was like, by the way, there will be some problems where it's a lot easier if you just change the basis. Hint, hint. And I don't quite know how to change basis. So, yeah. So, yeah. That's the thing. Oh my god, this is actually like illegible on this monitor, dude. What the hell? Can I just hide the sidebar? Yeah, there we go. Boom, now we have so much more real estate to work with. But oh my god. It's like illegible. I think I'll just full screen it. Tile window to the left, tile window to the right, yes. And then command 1, command 1. Do I really have to do that for each of these? Don't mind if I do. Okay, so now we have this going on. Look at that. Now we got dual screens, and then we can just swipe over to ChatGPT whenever we need to. Bing, bam, boom. Or I can have ChatGPT on my other monitor, my laptop screen. But for now, just give me a little bit of a break, okay? I need a little bit of a mental break before I jump right into it. Okay, dude. Just let me relax for a little bit mentally. So this is 1, 2... This is 3. So let's do a little thing. So perturbation theory is basically you take the Schrodinger equation, you Taylor expand it, and you find the nth order corrections to the energy eigenstates and to the wave functions, or to the eigenstates, I guess. Yeah, to the wave functions, to your states. So with perturbation theory, basically you do a whole bunch of derivations that starts off with these formulas of your zeroth, first, and second order corrections, where it's like h naught, psi, and 1 for your first order correction, plus h prime, psi n naught is equal to blah, blah, blah. The superscripts will add up to the order correction that you're working with. And you take those formulas, you do some manipulation where you multiply it by the left with your ground state, so psi n naught. And then you do some manipulations, you can express, and then it's actually pretty easy to express your first order energy correction as a inner product of psi n naught, psi n naught, h prime, psi n naught. That is your first order energy correction. Your first order wave function correction, or state correction, psi n1. So en1 was equal to that. So psi n1 would just be equal to, it's a summation, right? Psi n1. Yeah, because we don't do second order wave function. So your wave function, the way you get psi n1 is by doing this whole trick, Kronecker delta, blah, blah, blah. You do a summation, blah, blah, blah. And then what you get is that psi, you get the summation of m not equal to n, because you want to find, because basically what's happening is that for your first order wave function correction, what's happening is that you have some state here, and you're taking all of the other contributions from every other state at different energy levels. So you're just adding that to your new Hamiltonian that you get. And so psi n1 is going to be equal to a summation where m does not equal n, because your states are orthogonal, so you don't have any components that go into each other, whatever. So it's a summation of psi m not equal to n of the inner product of psi m naught and psi n naught with the operator h prime over the energies E n naught minus E m naught times the state, all of that times the state psi n naught, psi m naught, psi m naught. And then your second order energy correction, you basically get it. How do you get that? You get it from just taking your normal, your second order expansion, expressing it in terms of en2, and then you plug in psi n1. You plug the expression that you have for that, and then what you get is that en2 is equal to the summation, where m does not equal n, of the absolute value of psi m naught, the absolute value of the inner product of psi m naught with psi n naught of the Hamilton of h prime, the Hamiltonian, over en naught em naught. Is that what the second order is? Should have it here. Yeah, over en naught minus em naught. Yeah. Okay. Yeah. So that's your second order energy. And what's the intuition behind that? I think the intuition was like what? Your states are like pushing on each other or something like that. Like the second order correction, second order perturbation will always lower your energy pretty much, was what was happening. If you're in the ground state. If you're in the ground state, your second order correction will always lower your energies. Because, yeah. That's what we just learned, basically. Should I eat something? I'm really actually not hungry, but like I'm bored. I can't think of anything else to do, so I just want to eat. That's why I should be bulking eternally. The bulk never ends. What can I do to blow off some steam? Roblox? Shall we do Roblox? Should we do that? I feel like I can't like turn off my brain to Roblox, but if I unplug my monitor to plug in my PS5 and I play that, it's going to be a whole thing. Playing Call of Duty, that's going to be a whole thing. Oh my god. We should just not be lazy. We should just jump into it. The sooner we cover the homeworks, the better. Because there's just three things. There's conservation laws. So really we should just be focusing on what? This is not the right homework. Number 3, conservation laws. Yeah, so we should just be focusing on number 3. Pretty sure this is degenerate. And then all of homework. Second order perturbation. Yeah, all of homework 2. And I think all of homework 3. Am I correct in assuming that? Probably all of homework 3, because yeah, this is degenerate perturbation theory. Maybe not all of 3. You can ignore number 3, I guess. Number 4, we probably definitely won't need that. Number 5, maybe. But yeah, okay. Oh, I just don't want to jump into it. I don't want to jump into it. I want to take a little bit of a break. Guess I'm grabbing a glizzy if I'm ready to go. I'm feeling endless and a fro. You making it easy. This is speaking about growing and tell a lot about a man by the price of his clothes. I think since now there's nothing going on, we can throw on this. Let's turn down how much is being sent to the computer. I should adjust this eventually to where what I'm hearing and what you hear is the same thing, because right now it's slightly off. I just did my own botched kind of thing. Probably should not be doing this, but whatever. Yeah, okay. Adjusted it a little bit. Okay. I literally just have to jump into this. That's all I have to do. But what if I ate some pink salmon before then? Right? What if I ate some canned pink salmon? Don't you guys want to see that? You guys want to see me eat canned pink salmon? Should I take a little bit of a break and come back? If I take a little bit of a break and come back, then it's going to be 6 p.m. Bro. No, I shouldn't. I should just do this. I saw this TikTok where it was like, do it now, do it now, do it now. Just say that. Like when you wake up in the morning and you're feeling tired and you don't want to wake up, just say, do it now, and then do it. And if you just live by that, then you'll be good. I think I agree with that. I think I do agree with that. I might just have a quick snack. Can a guy not have a quick snack nowadays? I might just do that. I might have a quick snack. If I turn this all the way down, can you just stop hearing me? Do you stop hearing me? Or you can still hear me? Wait, you can actually still hear me. Wait. Oh, is it only dependent on this? Then what's up with the gain? What does the gain do? The gain... Oh, wait. If I... Oh, is this the only thing that gets sent out? Oh, so the whole time I've been controlling the wrong thing. Oh, you gotta control... Oh, I have to control the bottom knob to mute the microphone, not the top one. Good thing to know. Good thing to know. Sheesh. I think I'm gonna take a quick... I'm not that hungry though. I'm just trying to come up with reasons to make an excuse for whatever. Should I just eat some toast, some buttered toast, some toast with some nut butter and honey? Should we just do that real quick? Just to fuel the brain. Let's do that. Let's do that. I'm going to leave it here. I'm going to mute my mic, but you're still going to be able to see me. That's kind of weird, actually. Yeah, what I'm going to put on the screen is I'm just going to say taking a break. How should we do that? I guess should this be the break screen? Throw up an image maybe? Image. Browse. What image should we use? Should we use something aesthetic or something funny? Or maybe like a painting. Oh, we could use a painting. Or a Minecraft screenshot. I didn't set this to loop. Are you serious? Loop it. Turn that down. Yeah, let's just do a painting. Now we've got to really decrease the size of this a lot. And let's center it. How do you center it again? Holding Control, holding Alt. What makes it snap? Command, you can move it freely. I don't know what makes it snap. I guess we just have to eyeball it. Let's do that. Remove monitor screen. We can add text. BRB. Be right back. Yep. Okay. Then remove the webcam. Remove the to-do list. Should we still have the screen going? Yeah, okay, that's fine. All right. Quick break. Probably 30 minutes. And then we'll be right back. Ladies and gentlemen, we are back, and what I'm gonna do is I'm gonna pause this for a bit. So, here's the thing, right? So I was over here eating some nut butter on toast with some Trader Joe's honey, multi-floral clover, whatever, okay? But you know what I have in my cabinet that I've been wanting to try for a while? Wild caught Alaska pink salmon, boneless and skinless. It's in a can. So let's crack this open and let's try it out. Let's see how does it taste. That kind of thing. I'm actually very curious to try. I'm not going to put anything on it. I'm just going to eat it straight out of the can. We're going to see. So unfortunately, this is one of those cans where you have to use a can opener. There's no like pop top or anything, which kind of sucks. I always like it when they have a pop top, but let's open it up. So let's rotate this around so you can see me open it up. In the kitchen sink. Popped open, okay? Going to drain out some of the, I think it's in oil. It might be in water, I don't know, but draining some of it out. Okay. Rinse that off. It doesn't smell that great. I'm already kind of smelling a little bit of it. It's not too great, but you know what? We'll see truly just how it is. Yeah, let's try to open it. How the fuck? How the fuck? How am I supposed to open this? God damn it. Something very sharp. Pry it open. Bro, what the fuck? Okay, there we go. Pry it open. Pry it open. Okay. Okay. Oh. It looks and smells exactly like tuna. I think it's just tuna. It's pretty much just tuna in a fucking can. Let's plate it, I guess. Oosh. Alright. Toss this out. Let's rinse it out first. Boom. Wash our hands. Okay, hands washed, everything. We're all good to go. Now, let's try it out. Let me increase the gain on this here microphone because I'm going to be far away, so you can't really hear me. But now it looks like you can. So, this is what we have. Plated presentation. Doesn't look all that great, but I think it looks like salmon? I have no clue. Break it apart. There's some like spine there. You can kind of see it. If it'll focus. Yeah, there's like a spine bit there. In any case, let's try it out. Let's see how this is. I should get some salt, maybe? If this is really bad. Some sea salt. Just in case it's like under-seasoned or anything. Honestly, I'm not too... Like, I like eating sardines, I like eating canned tuna, that kind of stuff, so let's try it out. Let's see how it is. Yeah, it just smells like tuna. Okay. It's fine. It just tastes like tuna, honestly. Like, it's fine. It would probably go a lot better if it was like seasoned. So it's not enough salt, I would say. Let's break it up a little bit and then put some salt on it. Expose all these pieces real quick. Boom. Yes. So it is indeed boneless and skinless. And it might be a good source of omega-3s. I don't doubt that. But it doesn't taste incredible. But let's put it on a tortilla, corn tortilla, okay? I think we'll just use one. And we'll cook it on the stovetop, why not? For a real quick cook. Directly on the gas stove, flame it up. Enough on one side, flip it over. Cook it on another side. Oh. Yeah, this is okay. It's not that bad. Okay. That's that. Cooked up our tortilla. Real nice. Yeah, I could use a sauce as well. It's kind of dry. Like, if you just cook this like normal tuna, like if you just put like mayo in it and onions and stuff, it would taste really good. It's basically just like, I would assume, healthier tuna. I don't know if salmon has less mercury than tuna does. Not sure, actually. I know the healthiest thing that you can get is sardines. The healthiest and cheapest thing that you can get is sardines, since sardines are packed with omega-3s. However, they don't have a super high concentration of mercury in it. So I think salmon is also pretty good. But yeah, it's not bad. I wouldn't mind eating this. Like, consistently. Or especially in a situation if I didn't have any other options. I wouldn't hate this. By itself, I'd give this like a 6 out of 10. Yeah. Now let's try it with the tortilla. If I had this in the tortilla with like a sauce or something, this would definitely be pretty good. But just with tortilla, definite upgrade. Corn flour tortilla is the way to go. This was like some lemon juice, some salt, maybe like a sauce like mayo, like a bit of mayo, some cilantro, and some onions. This could go really good, actually. Pretty good. Pretty good. Not going to lie. Okay. And now, guess what is back on the agenda? Okay. Studying. That's right. You guessed correctly. If you guessed studying, you are correct. Right, I don't really like this hoodie. When I got it, it was a bit bigger, but because I got bigger, now it just makes me look fat. But I'm not fat, okay? I'm muscular. I'm muscular underneath all of this. Okay, I got, look at my traps. Yeah, you see that? Boom. That's muscle. Okay, and that's just my traps. But I gotta drink up. Jesus. Water. Brita water. What has been removed? Items removed from 15 from my folder. Someone's been transferring. Someone's making graphene field effect transistors as we speak. my sinus needs to become unmessed up. But it doesn't really matter. The most recent projects that I'm working on music-wise, the things that I have to do aren't really vocal related. They're more so mixing and adding additional, fleshing out the instrumental. But yeah, we just washed our hands. My hands are cold. I'm wearing gloves because my hands are cold. What else? I'm looking around the room desperately for like things that will allow me to procrastinate more. I'm like, oh, what else can I do to not have to do this work? But you know what? I will regret it so much if I didn't do this work to, like, I don't know, freaking, I don't even know. But yeah, so turn the music back on. Okay. Turn the music back on. I'm gonna pee real quick. Oh my god, dude, next week? Holy shit, I need to clean up my whole place. My whole place needs to be cleaned up. It's so messy right now. In there, oh my god, it's like a nightmare, dude. It's a nightmare. If you saw it, you'd be like, wow, you really are a mess. And I'd say, you know what? I am. What about it? What about it? What about it? You see how I'm just on my phone right now? Even though what I'm supposed to do right now is, you know, is a gym open on Monday? Let's Google. Not now. Google's always asking me. this next week, February 19th. Is it a holiday on Monday? What's going on Monday? I don't know why I'm being so tight-lipped about, like, yeah, I'm gonna look up Berkeley's academic calendar. Monday, February 19th is an academic and administrative holiday. Nice. So no class on Monday, February 19th. Oh, it's President's Day? Is it really? No way. That's crazy, yo. That's crazy, yo. So no class on Monday. So Monday I get to study even more. Okay, so I do get to prepare for this Math 104 midterm quite a bit. Real analysis. But yeah. Dude, I shouldn't... That salmon is actually... It's kind of upset my stomach. I wonder if I think the oil that they use is like some weird-ass oil. I'm very sensitive to seed oils, actually. That's my most Californian thing about me. And I really only started getting really sensitive to seed oils once I moved here. So, hey. Make of that what you will. Liberals. I don't think I took fish oil today. Let's take that. Because I think one of the things in seed oils is that they have too much omega-6. And so, too much, if you have like an imbalance in omega-3s versus omega-6s, then that causes inflammation, allegedly. So, let's take a balance. Actually, I just ate the salmon. That has a lot of omega-3s. Can you die from too much? Omega-3 is good for you. You can't possibly overdose on omega-3s. But okay. Let's look at number 3. Hello, where's number 3? Number 2. Number 3. Oh, I scrolled past number 3, didn't I? This is number 3. Okay. Let's read this. Let's read through this very carefully. Okay, let's be very careful when we read through this, ladies and gentlemen. Ladies and gentlemen, ladies and gentlemen, ladies and ladies and gentlemen, ladies and Oh my god, Sobe? Oh my god, do you guys remember Sobe? Holy shit. Is this still a thing? Oh my god. Is Sobe still around? Oh no, they've been discontinued. Yes, dude, this one? Oh my god, the Pina Colada Sobe? Holy shit, this was the bomb, bro. This Sobe? Oh my god. Strawberry daiquiri is also really good. Yeah, strawberry banana. Oh my god. Yo, to have yo, this is actually making me emotional. Yo, looking at Sobe, it's actually like making me emotional, dude. It's actually making me think of like a better time. Oh my god, is this still a thing? No. Dude, this shit was 62 grams of sugar. Holy shit, I can see why they went out of business, actually. Oh my god. A lot of vitamin C, though. Oh my god, that's a lot of sugar, man. Condensed skim milk? Really? Wow. But look at this. The ingredients are pretty clean, man. Damn. I need me a Sobe, man. Oh, man. Oh, dude. No way, man. If they reintroduce Sobe, man, the world would go back to being the way it is, man. I mean, what? The world will go back to the good times, okay? We're in the end times right now, but the world will be brought back to the good times if Sobe is back. They died during COVID due to material restrictions. Yeah, I couldn't find any either. Yeah, dude, they had glass bottles too. Oh my god. They have ones on eBay? An unopened glass bottle? Dude, that's crazy. This sure goes crazy hard though. This is pretty cool. It's an XL though. I can't. XL is too much. I would get this, man, but XL is a lot. Oh, this shirt is fire, bro. This shirt is fire. This shirt is so good. No way, dude. Damn. Okay. Okay, that's enough looking at Sobe. This is fire, though. I want to add that to my watch list. This is a fire gym shirt, dude. Wearing this to the gym? Sobe Adrenaline Rush. Man, that would be insane. That would be insane. This is also a pretty cool shirt. Add to watch list. No, don't add it to my cart. Can I remove that from my cart? Watch I accidentally buy this, dude. Remove. Dude, these AI videos, man. Oh my god. These AI videos that are coming out of like the prompts, holy shit, it's scary crazy, man. Scary crazy. Anyways. Meanwhile, I'm using ChatGPT. Okay. Let's not think about the possible ramifications that kind of technology can have in the future. Let's not think about that right now, just yet. Okay, what we're gonna do now is some work. Okay. Okay. Conservation laws. In class, we explained that if a system is invariant under a transformation, then the expectation of M is a conserved quantity. Yeah, if it's invariant under a transformation, then it's conserved. Now let us look at some specific Hamiltonians and ask which quantities are conserved. Specifically, we will consider 3 Hamiltonians describing the dynamics of an electron in 3 dimensions. As you already know, the charge of the electron is Q equals negative E, and it is a spin 1/2 particle. For each Hamiltonian, you will need to determine if the following quantities are conversed or not. Conserved, bro. Are conserved or not. Px, Py, Pz, P squared, Sx, Sy, Sz, Lx, Ly, Lz, L squared. Where Pj, Sj, and Lj are the expectation of the momentum, spin, and orbital angular momentum along the jth axis, respectively. The 2 other quantities are P squared equals P blah blah blah, and L squared equals that. Who is messaging me? Note, spin is an intrinsic quantity of the electron. S squared is always a conserved quantity. Okay. For each quantity, derive and or explain your answer. For A, that's A, C? Where do you start doing B? Oh, this is B, but he just called it C. Oh no, this is C. What the fuck? Wait, what am I looking at? Yeah, this is B, but he called it C, and then this is C. Okay. So the Hamiltonian of a free electron, H P squared over 2m, where P squared is equal to Px squared plus Py squared plus Pz squared, right? So we just have that HPJ is equal to 0 and HP squared is equal to 0 and HSJ is equal to 0, but why? Why is that? Dude, this solution is not making any sense. What are you What are you doing, man? All right, ChatGPT, do your magic. Desktop. Are these high res enough? They might not be high res enough. Let's take another screenshot a little bit more zoomed in. Yeah, this, that, and that. The first image is a problem relating to quantum mechanics and conserved quantities. The other two images are solutions for part A of that problem. Explain the solution for part A. While that's being worked out, I guess you know that momentum is just conserved. In a free electron, momentum is conserved. P momentum, right? Yeah, and then orbital angular momentum is the only thing that's like, is it conserved? Well, for a free electron, it's all conserved. He doesn't show the proof for this. Like, what is the point of this? What's the point of this? You're seeing if p squared and LZ commute with each other? You could have used any other operator. XPY, YPX, YPZ, XYZ, ZXY, YZX. I guess that's how we can remember it. In quantum mechanics, the conservation of a quantity is associated with the commutation of the Hamiltonian with the operator corresponding to that quantity. If the commutator that equals 0, where O is the operator, then that quantity is conserved. The provided solution seemed to calculate the commuters between the Hamiltonian of a free electron and the operators of momentum, spin, and orbital angular momentum. For part A, the solution goes through the following steps. The Hamiltonian for a free electron is given, which depends only on the momentum operator squared summed over the three spatial dimensions. It is stated that the commutator, implying that each component of the momentum is conserved. Like, I don't get this. This implies that p squared and LJ commute, which implies that the Hamiltonian LJ commute? Like, are you just saying that because the Hamiltonian commutes with p squared, then this operator will commute with the Hamiltonian? let's say I have operators A, B, B, and C. Is it true that if A, B, in this case, A, B, C. So if A commutes with B, then if A commutes with B, B commutes with C. Like, why are we seeing if these two things commute? Because our job is that you'll need to determine if the following quantities are conserved or not. What the fuck? Dude, what the fuck? What the fuck? Let's pull out the textbook, I guess. Conservation laws. Wow, it's just one page. Wow, this is great. Let's pull out the lecture notes. Wow, there's only one thing on conservation. That's incredible. That's great. So if H, if the Hamiltonian is invariant under U, then H and U equals 0. Note that if U is time independent, then according to the Ehrenfest theorem, d by dt of U is equal to I over H bar of the expectation of the commutation plus that, i.e. the expectation of U is a conserved quantity. What the fuck? This is the only thing on conservation? Did I write down any notes on this? Bro, what the fuck? The fuck? This is insane. What a fucking crazy thing. I don't get this. I don't get it. Someone's fucking stomping around upstairs. I'm just like triggered right now. I'm just angry. I'm a little upset because I'm trying to understand what conservation laws are, and instead all I'm getting is like this bullshit. Maybe I'm not opening my mind up enough. Like, how do you know these things are true? Like, how do you know that? How do you know that? Where do you get that from? Where do you get this from? This, you're using Ehrenfest's theorem? Why are you using that? Like, why? Why are you busting that out? I guess that, I mean, yeah, it's pretty obvious that would equal 0. Because all of them go to 0. Like, what the fuck? How do you know this? Oh, IH bar. How do you know this is IH bar? PYY, PXX, negative IH bar, negative IH bar. Like, how do you know this shit? How do you know this shit, bro? Okay, I guess that makes sense. Oh, did he just factor out the 2M and then didn't even fucking mention it? Okay. 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 Okay, so we've cracked the code on that one. Okay, so we know that, so this will commute. Since our Hamiltonian is equal to p squared over 2m, then p always commutes with itself. So then, and this is just inherent, the spin will always commute. So then now we have to see H and LJ. Does that commute? Well, this is just equivalent to p squared LJ. It would have been so easy. Okay, it would have been so easy. Like, why the frickety doodah wouldn't you just say? Like, when p squared in itself is an operator that's given. Oh, it's okay, it's okay. Whatever. And maybe I'm still wrong. Maybe that's not why they're using p squared, but you know what? It makes sense to me, so we're gonna do that. Let's say LJ, let's just use LZ, right? So p squared with LZ. And somehow we're supposed to know that LX is equal to YLZ, YPZ. Yes. YPZ plus ZPY. LY is equal to ZPX plus, and then XPZ, LZ is equal to XPY plus YPX, right? Yes. That's all minus. It's minus, not plus. Bruh. So p squared doesn't commute with LZ, so XPY minus YPX. Do these commute? I'm just going to get this problem wrong, the conservation problem. I'm just going to get this wrong. I think I'm just going to get this wrong. But let's try. Let's at least try before giving up, dude. Yeah, because you show that it commutes with one of them, then obviously it'll commute with the square of it. Oh boy. Oh boy. Oh boy. Isn't this just amazing? This is incredible. This is incredible. It's incredible. Boy, what is the future going to be? I think the future is going to be, I'm just thinking of the AI video thing. I think the future is probably going to be, it's probably going to value qualities related with discipline a lot more. Because I think in the future, people will want to gravitate. Well, this might not happen. But I think there will be a sect of people that will want to gravitate towards art that's made only by humans. And I think the self-discipline there will come from the fact of like, you know that if you want to record like a cool shot, you know that it's so easy to just type in that prompt and get a thing that looks very close to it. But there's something about filming that shot yourself and then like, you know, showing people like, hey, I did this and I filmed it myself. Whatever. Random thought. The only new feature is the dependence on Z. Most of the quantities are conserved. We will focus on that, on those that are not obviously conserved. So this is using Ehrenfest's theorem. HPZ over H bar is equal to I. You know that HPZ how the expectation value of HPZ Z, I guess because it's a sum of two things. Okay, so use the second part. So we know that this part is conserved, so we just focus on this part that isn't conserved. So Ehrenfest's theorem, d by dt of some operator is equal to, what is it, I, expectation value of the Hamiltonian with that operator, over h bar. So then d by dt of pz is going to be equal to I over h bar, the expectation value of h pz, right? Yeah. And we know that h is two things. P squared over 2m plus E naught Z. This is I over H bar. That commutes this part we don't know. Somehow you know that's IH bar. I guess I should have had these memorized, but I don't have them memorized. So we know that ZPZ is equal to IH bar, YPY is equal to negative IH bar, and XPX is equal to negative IH bar. I guess. Right? Doesn't he do this somewhere? Negative. Yeah, fuck this kind of question, dude.
So the other day I got an fender bender. This is the ultimate homemade BLT.
make no sense, but also kind of make a lot of sense for China. When you're here, people will stare at you if you aren't Asian, and it's very possible some of them have never seen a foreigner before. Like, you could be there first. China has so many Lay's flavors I've never heard of before, like Italian red meat, whatever these are, duck tongue, hot and sour lemon braised chicken feet. Speaking of, chicken feet is a super popular food, and even 7-Eleven sells them in little snack packages. Also, there are these massive markets that sell a ton of not real things, as you can see. If you're a foreigner visiting, sometimes people come up to you in tourist spots and ask if you're interested in buying not real things, and then they'll take you to wherever it is their not real things are. In China, there will be English translations that make no sense but are also kind of iconic. Sometimes they'll just straight up have the wrong spelling on, you know, really large public signs. Okay, this was savage. There was a pork store, and I guess they thought that these decorations would be the most appropriate thing for the store. People here are fiends for milk tea. This entire line, which we found out only after waiting in it for 30 minutes due to FOMO, was just for milk tea. That make no sense, but also kind of make a lot of sense for China. When you're here, people...
Damn, bro.
Impressive strength by this young athlete, but watch his feet. He could be bench pressing a lot more weight. You see, the best bench pressers in the world don't just lift with their arms and chest. They create full body tension and load their body like a spring. And no matter if you like your full foot into the ground like this or just your toes, pushing hard into the ground will help create optimal stiffness in your full body. If someone can come up and move your legs around, you're not tight enough. Here's another tip about leg drive that I first learned from 11-time powerlifting world champion Jen Thompson. It all starts at the very beginning. Get crazy tight and lock your feet hard into the ground. As you push the bar off your chest, you want to think leg drive. Now, a helpful tip is to drive your hips back towards the bar, not up off the bench. Practice the coordination and timing of this leg drive with partial reps during your warm-ups like this.
Okay. Oh my god. Oh no. I'm starting to lose steam. Should I focus on this anymore? It looks like it's just Ehrenfest theorem and a bunch of shit. The head of Ly is equal to this. Z XPZ, I guess because Ly is equal to Z PX XPZ. Yeah, and you know it'll commute with Z PX because there's a Z in there. So you just look at the XPZ part. Okay, sure. And Z XPZ, so ZPZ is equal to IH bar with X. It's another thing. Yeah. Okay, so I guess if you just memorize these things, then you're okay. He was also talking about changing basis. I don't know what the fuck. I don't know how the fuck you would change basis. I just assume he means that you're gonna look at different things. I don't know. It's probably gonna be some shit where it's like, oh, if you write LX in terms of the Z basis or something. Oh, if you write this in terms of this basis. I think this includes all the. I don't understand basis changes. I'm gonna be honest. I'm gonna be real. I'm gonna be real right now. Okay, I'm being real. I don't really understand basis change. I don't. Okay, I just don't. But anyway, yeah, all this work I did was wrong. It was wrong. Okay. Now, homework 2, I really do need to look at. Not the integrals, though. We don't care about solving these integrals. Okay, yeah, B. Blah, 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 B. En1 is equal to n v1. Psi n x squared times v. v1 is v1 given? v1 is given. Now, this problem is really easy. I don't know why I didn't do that. Yeah, and then it's just something as trivial as just solving an integral. But you have different values for when n is odd and n is even. Why is that? Because you have different wave functions for when n is odd and when n is even. So you would have to evaluate two integrals, yeah. Because you have psi n of x. This is just your potential, which is whatever. Your potential is your potential. Right? Yeah. Hey. Let's listen to some a little bit hype. We're 4 hours into the stream. I don't think they're gonna scan this. Okay, they're not gonna scan this. If you think they're gonna scan this, you're insane. I actually like, okay, a lot of people like to clown on Logic, okay, but some of his songs are really good. And I think this one is good. It's feel-good music, okay? Logic, he has feel-good songs. You play a song and you feel like you're invincible, you know? And I like that. You need that sometimes. And he's having fun. I don't think that was Logic who said this is a world premiere, but... And his beats, oh my god. Logic's really good songs, like, Logic either has really, really good songs or really, really mid songs. He's an extreme artist, okay? In the literal sense. And whenever he makes a really good song, whenever he makes a good song, it's really, really good. The beat is really good, his flow is good. His lyrics are whatever, but... Like, the flow is just good. Like, his flow is good. He has a good flow that matches the beat really well. Yeah, he knows how to play with flow. He's really good at that. Had a lot of guys want this year, like, he knows how to play with that. Like, his voice is almost like a hi-hat on a drum beat. Where, like, he knows how to play around. And then there's the beat switch. But he knows how to play around with his voice. Like, man, his flow is really good. I should do, like, music analysis streams. But, like, not theory. Just, the normal ways that you would analyze music. How a normal listener would analyze music. Let me get up on my MPC when I couldn't make a piece on the MVP on the main motherfucker, you're an NPC. Got him full of envy, the boy. Like, he knows what word choice to use as well. There's something in poetry. I think there's something called I forget the specific thing, but there's something to do with certain stresses that you put on words, okay? There are iambs. What is it? There's iambs, there's spondies. There's different ways that you can stress words, right? Iambs are basically like things where it's a stress, unstress, stress, unstress. So you're like, I am who you know will go to flow. Like, that's an I am. I am who you go to know to flow. Like, naturally, English-wise, it'll just flow like that. And then there's spondees where my heart was gone and you are hard, like something like that, you know? Where you stress the offbeat, basically. And that's like, if you don't understand how that works, then you, like, either, if you don't understand that intuitively or just like in like a studious sense, then you're not going to be able to write like good raps that like sound good. There are some raps where it's like people, their flow is just, it's not natural at all. It's like they're going into each other, like, it's just not great. But anyways, like, look at that, like all of the words he's choosing are just flowing into each other, man. It's good. His flow is good. Logic is pretty good. Okay, he has some bad songs, but his good songs are really good, man. Anyway, but yeah, if you want to find en1, that's really easy. We can even do that. So we know en1, we know the formula. Okay, it's just you take some state, h prime, another state, right? So that's just an integral of your state squared times your Hamiltonian dx from integration bounds. In this case, it's whatever it is. Let's say x and y, right? Yeah, and then you write it down. And then you have different wave functions for whether or not it's odd or even. Yep. I don't know what the fuck this J is, bro, but whatever. Why are you finding the first order correction? Oh, you also want to find psi n1 of x. If n is even, n1 is equal to the sum of k naught. Yeah, you know this is just going to be the Hamiltonian. No, this is the adjusted Hamiltonian, which you're given in the problem. Are you given that? Are you given h prime? No. No, we're not. I don't think we're given h prime. So how do you know this? If n is even, how do you know this? Where do you get this from? What? 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 Where did you get that from? I guess you just did the integral? Did you just like mentally did the integral? Oh, our h prime in this case is v1 of x. That's what it is. Why don't you just make that clear? Just make it, just write, it's one line, bro. It's one line. Just write one line. Oh, it's okay. It's not. I'm gonna go pee real quick. And you're gonna have to deal with it. There's nothing you can do about it. What can you do? All 0 people that are watching me? You can't do shit. Yeah, I'm a rebel. Dude, this live streaming shit is easy. The hard part is getting an audience. The easy part, it's easy to keep an audience entertained. Listen, if you're a people person like me, okay, it's very easy to keep an audience entertained. Okay, the hardest part is getting the audience. I need an audience. I need some water. Something came over me. Way too high to simmer down. Might as well overheat. Too close for comfort. Is blood rush my favorite vein? Heartbeat racing like a youngest. I just need you to want me. Am I asking too much? Bro, my new shoes are getting shipped. I need those new shoes now. Watch, by the time I get them, I got new shoes, they're waterproof. But I know that by the time I get them, like, the rain would have stopped. Raindrops keep falling on my head. Blah, 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 blah. Wah, 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 wah. Wah, 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 wah. Look at this. That's my dog. Look at him, he's so funny. He's such a funny dog. What a funny dog. Look at him, he's such a funny dog. He's a funny dog. He looks kind of messed up in that photo. Like asymmetric type beat, but whatever it is what it is. Whatever it is what it is. It is whatever it is. But today's a good day, good day, good day. Okay. So, this state calculation, I think I should go through this one more carefully. So, some psi n1, right? That's just going to be equal to summation of m not equal to n of psi m naught h prime psi n naught over e n minus e m naught times psi m naught, right? That's what this is, right? That's what psi n1 is, right? Or no? Yeah, that's what it is. That's what it is, I'm pretty sure. That's what the first order correction to it is. Yeah, it is. That's where he gets his K. So equal to m not equal to n of psi m naught, and then we insert this potential, this v1x, which v1x, what is that given as? v1x is alpha cosine of x pi over L with the first psi n naught all over e n naught minus e m naught. Are we given? Yes, we are given the ground state energy. Ground state energy is given. Ground state energy is given. Yes, 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 yes. I hate how this dude writes his goddamn wave functions, bro. He writes these states as just like n and k, bro. I know it looks cleaner and it's quicker to write, whatever, but it's more confusing. Oh. Okay, so check it out. We'll insert that psi m naught somewhere randomly over here. Actually, let's flip the page over and let's do this. Psi n1 is going to be equal to the summation of m not equal to n psi m naught alpha cosine pi x over L psi n naught. Well, we know it's psi. Well, we haven't split this into the en1 or e1 0 of n squared minus m squared, right? Yeah. If m is even, if n is even, not equal to n, psi m of 0, well, we know what these are. We just have to replace the index instead. As you know, it's I1. Oh, I guess it's this integral. Well, we know what these are. Okay, it's integral. You do alpha cosine, but not x. Instead of x, it's now m and n. Like, what the fuck is this, bro? What the fuck? Can you just like do this, please? Pretty sure it's just the wave function. Oh, I'm not copying. The wave function is this. That is not the wave function. That is the potential that it's in. So we will erase that. Yeah, so psi m 0 is going to be the complex conjugate, but it's real, so it's not complex. So 2 over L, what is this? Cosine m x pi over L times alpha cosine of pi x over L times square root of 2 over L cosine of n x pi over L. That's what that is. And that's exactly what this integral is. So it's some wacky integral over e1 naught n squared minus m squared. That's what this is, right? So if n is odd, then this is just equal to the summation of m, which is odd, not equal to n, of the integral of... You get the picture. Okay, yeah, that was actually very easy. Without doing any math, explain if the resultant states are normalized up to those corrections? Yes. Because n and n naught plus n1 times that. One plus the real part of that plus that. That doesn't make any sense. I don't get that. I should probably not be using paper. I should probably just do this on my iPad so I can show you guys the magic. You guys are missing out on what the magic is. You guys are missing out on the magic of this all. How could I forget? Plug, 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 plug. Hey, yo, turn this shit on. Hey, Soundwave, turn that shit up. Tell me who the bitch hating on me. To Pimp a Butterfly, another classic MC. Here we go. Here we go. We're doing this. Yes, we are. Yes, indeed, we're doing this. So we have, yeah, you can see it. Look at that. No setup needed. It just automatically pops up. So we have what? N with N, which is just equal to N naught plus N1 plus some correction times N naught plus N1 plus some correction. And we're saying, so this with this is going to give us 1. That with that is going to give us 1. Or wait. So that with that is going to give us 1. This with this is going to give us 0. And this with this is just going to give us something. So this is going to be 1 times 0 plus oh my god, how do you do this? Yeah, it's 1 plus 0 plus question mark. Oh my god, how do you factor? How do you do this? It's that plus that, so it's x squared plus xy plus yx plus y squared. That's how you factor, right? So it's when you have 3, it's that, so it's this plus this. Yeah, you just plus everything. So it's 1 plus 0 plus whatever this is. I don't even know what this is. Plus N1 with that is going to be 0 plus 1 plus N1 with order 2. But the solution is not doing it. What is it doing? It's saying that 1 plus the real part of N naught N1. Oh, I guess you can't make assumptions about it being orthogonal. Wait, no, you do. You literally do. That's how he gets equals 0. Plus that. I don't know. Whatever, dude. I'm not sure. Whatever, bro. Part D, repeat the calculation for the second one. That's really easy. It's the same thing. Did he just copy and paste the page? No, this is him doing it for the second one. Yeah. Without doing any math, explain if the resultant states are normalized. What the fuck? Why does he have an F? What the fuck? It's very clearly just like D and E. D. What is this then? It's just a random page. Oh, I think this is supposed to be D. I don't even know, but yeah, we know how to do it for V2. It's the same procedure. This thing, again, I don't get how he's getting that. I guess because these will be 1. So it's just that, and then that, and that. Like, why does he, like, I don't get it. Time to ask ChatGPT to break this down. Break it down. Break it down now, y'all. Break down the steps for this. How does he get 1 plus real of N naught N1 plus O2, right? O alpha squared. This is no help. Yep. No help. No help. It's no help. What does it say? Without doing any math, explaining the resultant states are normalized. Yeah, I don't know how else you would do that. Anyways. Derive En2 for the infinite square well. Well, for infinite square well, you know that there's some quantities. Yeah, En2 is this thing over here. We're given that H prime is this garbage. Yeah. Given that H prime is this garbage for the infinite square well. So we know that the wave functions for the infinite square well. How do you know the wave functions for the infinite square well? Yeah, I don't remember them. But I guess you're just supposed to remember it. And if it's n is equal to even, then it's 0 because you do an odd integral. If n is odd, then it's not. I don't know. I don't know. LOL, tay random. Should we actually just work this out? No. I know what these are. En2, I know what this is. This is the sum of m not equal to n of psi m 0 h prime psi n 0 amplitude squared over e n 0 minus e m 0. Yeah, it's just that. Yeah. Yeah, I know this. I know this. I know what this is. 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 The real test is, can we derive this? Let's see if we can derive these again. So you start off with your normal. I hope to God there's a question on deriving this shit, dude, because then I would fucking kill it. But I feel like there's not going to be a question on deriving it, though. You start off with that, and then you do some Taylor expansion. This is the 0th order, the 1st order. So with this, you know that you know that when h naught hits this, it'll just give that, which then ends up canceling out that with that. No, not yet. No, not yet, young Padawan, not yet. So what we do now is we multiply by psi n naught, which we are totally able to do. Yeah, because we don't know this. This we don't know, because that's the first order approximation of the wave function. We only know this is all we know. So that's going to be that plus that. And this is, we already know that this is the term for en1. Yeah, okay. We know how to do this. That will hit that, and that'll give us en naught, and that'll cancel out that term that's over there. So we know how to do that. And then in terms of deriving, let's fully write it out. How would we derive psi n1? It's a constant, so we can just pull that out. Forgot. So what is this going to leave us with? En1 psi n1. Well, now we know that's en1 as well. Okay, before we go too off the deep end with deriving this, we can just kind of remember that this is a sum of n not equal to n. Like, we know that this is what it is. Oh. Right, plus dot, dot, dot. We know that we can write this in terms of something like this. Right, so now we need to find what this is. How do we find what that is again? Damn, I forget. Ooh. Ooh. Okay, this is wrong. What we do is we go from this equation. Always just start from that. Okay, let's always just start from these first ordered equations. Right? Starting from this, right? Then we can just do this. Let's collect like terms, right? So then we have h naught minus e naught, en naught, psi n of 1 is equal to en1 minus h prime psi n naught. So now we have it in terms of this, and I guess we can just plug in. We can plug in what psi n1 is. So h naught minus en naught. I got that wrong. It's actually an M. There's an M in that index. Now what? Now I have to cheat a little bit to look at what the hell do we do? Oh, then you have to take this magical step, just multiply by some arbitrary wave function. So then we have this. We can pull out the summation as well. Pull out the summation. Right, and now we have CP H naught En naught psi M naught equal to psi P naught En1 minus H prime psi N naught. We can just rewrite this as this. Right, and okay. Now we have something that we can hit this with. So now this is this psi P em naught minus en naught psi m naught. And now we can pull this, we can pull that bad boy out. So let's just pull it out. Em naught minus en naught. So we've pulled this out, and now I have psi p naught psi m naught is equal to negative psi p naught h prime minus en naught psi n naught. Now we have that. Okay. We can also totally do this. This is legal to do. Okay. Oh shit, this is an EN1. That is a bad mistake to make. Bad mistake to make. EN1. This is a totally legal move that we can do, right? Yes. So now we have this. And now we have some conditions where 1, we can set P equals M. 2, we can set P not equal to M. To N. Or is it, yeah, it's N. These are where the nuances come in. I could totally see this being a question on the fucking midterm, bro. Please make this a question on the midterm. Even if it's not, we're still going to run through this. And then after this, we'll look through number 3, I guess. The modified harmonic oscillator or whatever the hell. And we'll look at homework 3. Because homework 3, we're probably definitely going to have to write some matrix. And I don't know how to do that. So with case 1, P equals N. Then you have psi N. Psi M of 0. And this equals 0 because M cannot equal N, right? Therefore, you have En 1 would be equal to psi N naught H prime psi N naught right, that's all fine and dandy, but we can't get the first order correction. For the first order correction, what we'll need is P not equal to N, and then psi P of 0, psi M of 0. When P equals M, this equals 1. When P does not equal M, this equals 0. So this is a delta P M, Kronecker delta, right? And then psi P of 0, psi N of 0, that is equal to 0 because P does not equal N. That's why. Okay, so now we can go back to this. Okay. So now we have this, right? Delta PM And we know that this now goes to 0. I guess not like that. This is equal to 0, so then this is completely just 0. So now we can solve for CMN, right? There's some limitation the delta gives. So now we have CMN is equal to negative psi p naught h prime psi n naught over E m naught minus E n naught. Because this term forces m to go to n. Yeah, this I don't quite get, and then you have this term, and then you can plug that back in. So now you have the summation. Right, you have this times this times that. Can flip this in the bottom, and then that's psi m of 0. And that is that. Bob's your uncle. We just discovered that. And then for EN2, how do you know the second level degeneracy? Second level degeneracy, or the second order degenerate perturbation theory, I guess. Yeah, you do the exact same thing. So you always want to start from these things. Start here when finding EN1, psi N1, EN2. I guess we'll include the second order somewhere here. Which is just going to be this. There's only one perturbation. That's going to be 1. That's going to be that. So for EN2, you would just work from here. So let's multiply by psi and naught again. Our trusty method of getting things to work out. Can factor out the EN naught here. And you can already see where this is going, can't you? I know you can. I know you can already see where this is going. Because check this out. This hits that, becomes EN naught. So then that and that cancel out. The H prime you still keep. Can't believe I forgot this. I think it's that, right? Yeah. That equals 1. So then now you have... This is equal to en1. That's going to be equal to 0, right? So it just gets rid of that. So then en2. Yeah, and then you just plug in what psi n of 1 is. Right? This is what you get, right? Yeah, en2 is equal to this. Yes. Plug in psi n of 1. Yeah. Yeah, baby. You plug in psi n of 1 and then you'll get it. Boom! So that's all of our perturbation derived. Please just put that problem on. If you just put the derivation of it on, it's such an easy question. It's such a lazy question to just give. You know, it's an easy question to give. And on top of that, okay, on top of that, it's an easy question to come up with, and it's fairly difficult to derive, especially if you're talking about the first order wave function. That requires a whole lot of steps. But if you remember those steps, and if you know where it comes from, then you're all good. Okay. Gonna use the bathroom again. Whew. Hello. Hello, everybody. My name is Markiplier. Hello, everybody. My name is Markiplier. Okay, we went over deriving all that garbage. Okay, so now we're just gonna go. Should we even look at this? The modified harmonic oscillator. We should just not even waste our time on this, dude. Watch it be on the freaking midterm. I think it's better to spend my mental energy looking at homework 3 rather than focusing on homework 2, because homework 3 deals with the degenerate perturbation theory, which I should go over. Okay, so it says calculate the first order correction to the energy to the states with unperturbed energy E0 equals E5. Boy, what the hell? What the fuck? What the fuck? Holy shit. This shit is fucking crazy. Oh my god. Ah, okay, I got this right. Thank God. Okay, bro, what? What the fuck? Oh, no, no, no. Bro, I've been live for 5 hours? Are you serious, dude? Oh, 5 hours. It's a long time. It's a long time to be live for. Well, you know what this shows me? This shows me that my previous times where I was like, oh, I can only get in 2 hours of deep study work. That was just excuses, bro. Pure excuses. Because I can get in more than 2 hours. Okay, I'm doing that right now. That's literally what I'm doing right now. Getting in more than 2 hours. I don't think that fuzz is inherent to the... Yeah, okay. Huh. So I can always turn that up. Good to know. Anyway, boy, oh boy. Okay, what's happening here? What's going on here? What's going on, guys? What's going on, guys? What's happening? What's happening, fellas? What's going on, guys? So you have a 2D, infinite, whatever. Calculate the first order correction to the energy to states with unperturbed energy. So ENN prime. Yeah, you're given that. How do you know this? How do you know this? Just give me my money. How do you know this? How do you know this? Is equal to 5 E naught. Oh. I don't know how you know this. Also, why is he doing n prime n when it's n prime, bro? Okay, let's work this out, I guess. So we have en prime n is equal to en naught n squared plus n squared. And we know that E naught somehow you're just supposed to know that this is just equal to 1, 2, 2, 1. I don't know how, but you just know that, I guess. So then your W, which is a 2 by 2 matrix, H11, H12, H21, H22. Pretty sure it should be like this, right? Row by column. This is row 1, this is column 1, 2. Yeah, it should be like this. So then this is H11. So this is H n prime n basically. And with n prime is 1, you choose first thing 1. When n is 1, you choose 1. Or 2. N prime and n. So you want the first one of each one. So there's going to be 1, 2, H prime 1, 2, 1, 2. So you want 1, 1, 2, 1. What the fuck? I'm like 99% sure he did this wrong, dude. What the fuck? So those are equal to 0. So then if your Hamiltonian is comprised of off-diagonal elements. Oh, what's the thing again? What's the thing that he was talking about? What's the thing he was talking about? Yeah, so since the Hamiltonian, since the new Hamiltonian has diagonals that are 0, so it's only off-diagonal elements, so it has non-zero off-diagonal elements, then that means that there's some sort of issue? Does that mean then the matrix, so the matrix element is comprised of off-diagonal components? Pretty sure he got them mixed up, bro. I'm like pretty sure he got them mixed up. Yeah, I guess it doesn't matter if you get them mixed up because then you could just factor them out because they're going to be the same thing. I'm pretty sure this is going to be 1, 1. How the fuck is it not 1, 1? This would only be true if it was n prime that he was talking about. This would only be true if it was n prime. Because n prime, 1, 1, that would give you 1. No, it's the same thing. No, it's not. Because 1, 2. Yeah, it'd be the same thing. What the fuck? Is it column row? Is it really column row? I thought it was row column. Column by row? How do you label matrix elements? One, 1, 1, 2, 1, 3. Yes. 2, 1, 3, 1. Yes. 1, 2, 2, 1. 2, 1, 1, 2. What the fuck? What the fuck? What the fuck? How is he doing this? This shit has to be wrong. So I get how that's 1, 2, right? What about for this one? Right, so it's H22, so it'd be 2, 1. Yeah. 2, 1. So where is he getting the other random bullshit, dude? Where is he getting it? And 1, 2 is equal to 2, 1? How do you know it's odd and parity? Oh, I don't know. I don't know. I do not know. N prime. Oh my god. Oh my god. How do you know they have definite parity, bro? Oh, nothing is explained. What's the Assassin's Creed quote? Nothing is permitted? What is it? Oh, this is the way the lecture notes are. Put this on this page, please. What is it? Nothing is true, everything is permitted? Yeah. Nothing is true. Everything is permitted. Okay, let's look at how did we go about doing this W shit? Like, I'm just not understanding this, dude. I'm not getting it. All possible pairs of quantum numbers such that nx squared plus ny squared equals 5? Oh. Wait, what? Okay, that makes sense. Yeah, so then if 1 plus 2 equals 5, and then 2 squared plus 1 squared equals 5. Okay. So that gives you the quantum numbers. Oh, you fucked up the fucking formatting. You messed up the latex formatting. Please fix it and never make this mistake again in the future, you horrible, useless bot. It fucked it up again. It fucked it up again. Oh my god. Oh my god. Oh my god. Oh my god. I know, I'm being really mean to this bot. Oh, it messed it up again! Oh, oh, oh. No, that doesn't make sense. Wait, 1, 1. It's 1, 1. Wait. It does make sense. Wait, 2, 2. So it's 2, 1, 2, 1. Yeah. 1, 2. 1, 2 would be in this one and then this one. Or wait. Yeah, 2, 1, 1, 2, right? 1, 2. I mean, you do 1. And then you put 2, which is 2, 1. And then 2, 1 means that you would put 2, 1. And then 1, 2. Yeah, I'm pretty sure that he just mixed it up. The off-diagonal elements. But it doesn't matter if you mix up the off-diagonal elements. Okay, that's it. This just refers to like this one. Okay, yeah. So wait. That would refer to this one. That would refer to this one. That would refer to this one. The 2 refers to that one. So the 2's refer to that one. Oh my god. Okay, it makes sense now. It makes sense. Makes sense. Okay, so now you have that. And apparently because it's odd parity. So now you have to calculate these. Yeah, so 1, 2, 2, 1. I guess you know what H prime is, so you can pull it out. And then you have 1, 2, 2, 1. 1, 2. 2, 1. What the fuck? Why is it squared, dude? Why is it squared? Stop! Don't make your solutions as elegant and as short as possible. Make your solutions long. Make it long. Make it clear what's going on. Oh my god, okay. Lambda E1. Right? Right, dude. Right on, dude. Yeah, dude. See, this says XY. But like, there's no Y's here. Where'd the Y's go? Like, why are you just saying X, bro? That's what I don't get. So what does he have? He has 2 over L, integral of negative L over 2 dx, cosine of x pi over L, sine of 2x pi over L, sine of x pi over L. All of that squared. So what is this? Cosine of x pi is psi n of 0 for odd n. I guess because it's odd? That's the Hamiltonian, and then that's psi n for n equals 2. What are the commutator relationships that I need to remember? Yeah, I need to keep this. I need to look at that tomorrow. It is 8 p.m. right now. I need to do dishes and go to sleep. But I'm not even finished with 3. I still need to do 2. Still need to do 3 we can ignore. 4 we can ignore. 5 we probably can't ignore. Breathe in, breathe out.
excited?
You know me, I'm just trying to get in and keep rep.
I need you to talk this time to me now, bro.
You know I'm shy as fuck, you know.
I know, Jordan. All right, yo, Cardi, oh, I know, Jordan, I know. All right, yo, Cardi, I'm gonna call you later. We're gonna get part 2 in motion, okay?
See you later.
All right, bye. Yo, part 2, chat.
Okay. Dopamine recharge. Oh. Oh, please. Help me. Help me. You know the Half-Life 2, the head crab people. Oh man, that's how I'm feeling on the inside. But anyway, 1, 2, 2, 1 is equal to that. So then 2, 1, what is it? 2, 1, 1, 2 would be equal to the same thing because it comprises of the same integral. Guess I'm grabbing the Cleasy if I'm ready to go. Make it easy if you speak to a crowd. Tell a lot about a man by the price of its clothes. So this matrix is not true. This is just incorrect. This matrix is not true. Because this has lambda E1 over 4. This one has L over 4. Like, there is no L term in here, bro. Like, I think you made a mistake. I think this is squared. So it's L squared over L. So that would cancel out to leave 1 L. I think you made a mistake in your algebra, bro. Anyway. Then the determinant. V times the identity. Yeah, it is equal to that. So the determinant is just going to be that times that. Yep. V squared minus that equals 0. So an E1. What happened to this new? What happened to this? Where'd that go? Where'd you put it? What the fuck, man? Are we just setting new equal to 0? Or like what? I don't know. I'm just gonna get that problem wrong. Yeah, I think 6 hours is my limit. I think 6 hours is the new limit. 6 hours is the new limit of how long you can study. Technically 5. We've been studying for 5 hours because you include an hour for all the breaks and the gaggles and goggles that we did. Okay. But anyways. Okay, so we have this. We have a bunch of raising and lowering operators. Yeah, okay. I'm pretty sure I fucking did that, bro. What the fuck? N prime minus 1. Square root of n prime n. Okay, yeah, he just combined these into like one thing and then put those scalars together. Yeah, okay. Okay. This is not right. It's gonna be 1 1 1 1. 1 2 would be 1 1 2 0. This will be 1 1 0 2. Right? W1 3 is. Yeah, so all the diagonals are 0. I don't get it. I don't get it. I don't get it, but it's okay. I was close, I guess. I don't know, dude. I don't know. I don't know. I kind of did a stupid mistake here, I think. No, I think that works out. I think it works out. Yeah, because it's 2 to the 1/2 over 2 to the 1, 2 to the -1. Yeah, should be that. Should work out. Oh, 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 darling, please believe me. Ah, so that new is E1. So why the fuck did you put new instead of E1? You shithead, bro. You absolute fucking... I'm being really mean. I'm sorry. I should not be this mean. It's just really frustrating. If you're writing solutions, you should make your solutions as clear as possible. You should really just make them as clear as possible. And you could say, well, it's your fault for being a shitty student. You don't understand shit. That's not my... Like, the onus should not be on me to have to decrypt every single fucking thing you say, okay? If you write your solutions to be as short and as clean as possible, it's gonna take me so much longer to go through it because I've never gone through this in my entire life. You realize this is the first time I'm ever seeing this in my entire fucking life. I'm really frustrated right now. That's okay. Dude, okay. Yeah, I'm frustrated. Yes, I am frustrated. Yeah, that does become quite simple, huh? Yeah, you take the... What is it? Like, you block off that, take the determinant of that, block off that, take the determinant of that, block off that, take the determinant of that. Why do you get 3 values for what E could be? Is it because it's cubed? I don't... What the fuck? How are you getting 3 values for what E could be? Because E is equal to 0 plus and minus? Okay. Whatever, dude. the hell is the
we're now noticing is that in these formulas, what we're summing over in these formulas are the off-diagonal matrix elements of the perturbation. What a funny thing to notice. All right, I'm just telling you, there it is. These sums, we're summing over the off-diagonal matrix elements. So we're doing sort of like this weird sum over off-diagonal matrix elements of the perturbation. And so the point I want to make is that what we have is if we have a degenerate subspace, then the whole point is to see in this little degenerate subspace what is the value of these off-diagonal matrix elements. So let's restrict ourselves to the degenerate subspace, because the degenerate subspace is the only place where we're going to get these singularities, these infinities. And so we got to fix it. The problem is lying in the degenerate subspace, and so the problem lies there. It's in the degenerate subspace. That's where the problem lies. And so basically, if the off-diagonal matrix elements in the degenerate subspace are 0, then there's no problem. The formulas work. But now let's go to the horrible case. But on the other hand, if psi m naught, horrible problem that I have these formulas, these things are true at the same time, then you are screwed, states. Formulas are fixed. I want you to look at this 4 up again. That is right. But then, so here's the question. Okay, psi m naught. Good, but we have finite choice. There's of course it would do that. I mean, this matrix elements are 0. That means that your matrix is diagonal. It's diagonal. Because if your off-diagonal matrix elements are 0, well, in the degenerate subspace, and that's it. That is degenerate perturbation theory. It's just so simple. It's like sort of simple and obvious. You know, it's like there's no real trick to it.
Yeah, so what it is you're constructing this matrix, and you look at the off-diagonal elements. If the off-diagonal elements are non-zero, then you have a problem. And so in order to fix it, then you need to find a basis where this goes to 0. And to find the basis, you just solve the determinant formula. Okay.
We're just trying to make the stupid formulas work. And the only way we can make the stupid formulas work is to diagonalize h prime in the degenerate subspace. If we diagonalize h prime in the degenerate subspace, the formulas work.
Yeah, you're just trying to make the formulas work. This isn't changing anything about the actual, like, what you have going on. You're just trying to make the formulas apply for this. Okay, you know what? Conceptually, I understand it. So here's the thing. He said that the test would be on conceptuals, not so much on calculations. So I'm not going to worry about these calculations, okay? Let me not worry about these calculations. I'm done. Unplug. No more iPad. Bye-bye. Say bye to iPad. Timmy, say bye to the iPad. Okay, guys, I've had enough. We're officially at the 6-hour mark. Can you believe it? Okay, this has been quite a popping study session. Okay, we've got quite a few. We had a few rage moments, I'm not gonna lie, okay? But those are not at the fault of mine. They're at the fault of whoever is writing these solutions. Because let me just explain it simply and calmly, okay? If you are teaching kids, if you're teaching people, all right, let's not use any normative terms here. If you're teaching people an entirely new thing that they've never seen before, right? And if you're going to write solutions for problems that they've solved and they probably got wrong, you would want those solutions to be as simple and as, like, understandably stated as possible. So I would never teach algebra, okay? Here's an example. Here's a definitive example of what I'm talking about, okay? If I was teaching algebra to someone for the first time, I would never do something like this. If I was teaching, like, factoring, I would never say, like, okay, so we have this, and this is just equal to x squared plus 2yx plus y squared. I would never do this. But this is essentially what every single goddamn teacher does. What you should do instead, right, is teach it like this. Whoops. What you should teach instead is like this. You teach it like this. you teach it like this. X plus y, x plus y. And the way I would teach it is by laying it out very clearly. So I would write something like x squared plus xy plus yx plus y squared. And here, what I would include as well is like something like this to be like, oh, x squared times x, that's where we get this. And then, you know, x times xy, that's where we get this. And then, you know, y times x, that's where we get this. And y times y, that's where we get this. And then I would say something like, okay, and then when you group this together, notice that, you know, notice that these two are equivalent, right? So then when we add two equivalent things together, that just means that we have 2 of xy. We can interchange x and y or whatever, and then plus y squared. And then I'd be like, usually we also want to collect it in terms of like lowering exponents. So we put the highest exponents here. So we order it in descending exponents, and boom, that's how we do it. That's how I would teach this. So many of my classes, though, the way that they teach it is just writing this. Like, there's 2 ways to teach it. Way 1 and way 2. And all of my classes are teaching it in way 2, which is fine and dandy. Like, if you've seen this before and then you look at this, you're like, oh yeah, 2 is so obvious, is it not? But the problem is that you've never seen this before. So when you look at this, you're like, wait, what? And then you have to spend like an hour being like, wait, what's going on here? And you have to be like, oh, I guess we're doing this. And then you're like, wait, but how do we get this? Oh, it's because these two are the same. Like, it takes the instructor 1 extra minute to write out these extra steps. Let's be generous. 5 extra minutes to write out these extra steps, right? At most, 5 more minutes it takes the instructor to write these steps. Why not just do that? It takes the student like an hour to figure out this by themselves. It's crazy. I don't understand why you would do this. Why do this? Why? So this is something most of you kiddies, most of you fellas out there can understand, okay? Because most of us know how to do high school level algebra, or I guess middle school level algebra, whatever. Most of us know how to do middle school level algebra. Now take this and just make the concept higher. So now we're talking about quantum mechanics. Now we're talking about perturbation theory and quantum mechanics, right? And instead of taking this route, my current professor takes that route, which is really annoying, okay? It almost just makes me like want to do a PhD in physics out of spite, just so I can like be one of the good professors, okay? I can be one of the good ones. But I also think at a certain level, if I see you teaching like this, not only do I think that you're a bad lecturer, but I think that you don't understand fundamentally the material. Because to be able to do something like this, you need to understand, well, not fundamentally, not in a literal sense, but you need to understand at a foundational level, like this whole technique of like how foiling works or whatever, or how the distributive property works in mathematics. You need to understand how the distributive property works in order to break down a problem in this way. If you don't understand distributive property and you just kind of like, if you just think like, oh, like, I don't know, there's 2 x's, 2 y's, and then there's like 2 xy's. If you think of like something in like that, some stupid way to come up with this, then that explains why you're teaching like this, because you don't know how to do this. You don't even know how to do this, okay? Which means that your degree or your PhD that you got is worthless, because well, it's not worthless because you're doing it for research, I guess. But if you at all want to pride yourself on, you know, being a professor, which I think you should if you're a professor, it's like it's like the highest level you can reach in academia, you know, professor. It's like the end goal. Like if you at all pride yourself on being a professor, you should be able to do this. And if you can't do that, then just quit, bro. Just stop. Just stop teaching. Let someone else teach, okay? Give it to someone else. But anyways, that's it. That's it for today, guys. That is it for today. We're done. We're done. I'm gonna go do the dishes. I'm gonna go shower. I'm gonna get a restful sleep. The only thing I need to memorize are these commutators. Lx, Ly, Lz. Lx is equal to y, p, z, minus, and then you flip it around, z, py, and so on and so forth. The commutator of z, p, z is equal to I h bar, and with all the other ones, it's negative I h bar, okay? And that just kind of makes sense because we define spin as being in z axis. So the commutator is going to be positive in the z axis, negative in the other ones. And then there's Ehrenfest theorem, I guess, which is something that tells you about whether or not it's conserved, I guess. I should have a note on this. This is one thing that I should hopefully have a note on. Lecture. Okay, it's not on day 1. Yeah, it shows that an operator is conserved with time. Okay, that's that. Well, guys, it's the end of the road. Any last words? Nope. Nope. Nuh-uh. Nada. Bro, this dude has not even made one announcement about midterms. Bro, fuck this. Okay. Whatever. Professor of my class, if you're seeing this, I don't mean this as hate. Okay, again, there might be another student who feels completely differently, and I recognize that. Although I do feel like I do have some objective criticisms. Will I say them to you? Probably not. Because I don't want you to get some bad idea, and then suddenly my grade is affected in some way. I'd rather just play it cool. Just play it chill. Play it chill. PlayStation. 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 I'm always doing it too flat. PlayStation. PlayStation. Close.